Assalamu alaikum, ladies and gentlemen. Welcome back to another live stream. Okay, so it's been a while. Let me just please share the live stream on my Discord. Please join my Discord server. You can find the link down in the description below. It's basically just discord.kodotaku.com and it'll get you there. Alright, so today it's just gonna be a chill stream. It's not really much about, we're gonna be doing Vulkan, yeah, but like I mostly start streaming to just, answer your questions and just chat pretty much. And yeah, and just bike shed some C++. Alright, so alright, let me just share the stream here. One. Hopefully everything is fine. Let's see if the stream is good. Just gonna pop out the chat real quick here. So I don't usually like live stream in the day. I usually only live stream at night. But today I kind of got the opportunity to live stream at the day for the first time. So yeah. Alright, so I think we could start already pretty much. Can someone confirm that the live stream is fine? Alright, I guess I'll just start already. So right now I'm not gonna start this live stream from scratch. I already have some few things that I'm gonna explain here. Like, of course, I'm using VC package. I'm just pulling in SDL3 package with Vulkan. So basically, C-Line gives me VC package easily here. Like, I could easily just make it manifest mode and then like search for any package. Let's say I want shader C. I could just search for shader C. Click it, add to VC package, and there you go, done. I have the library in. No need to do anything crazy. I also have GLM in for now. I'm gonna be covering modern Vulkan extensions like push descriptors to make Vulkan way easier. I'm also going to cover dynamic rendering and some runtime shader compilation too using shader C. So a lot of bag of tricks that I learned these days pretty much. I was like exploring a lot of C++ stuff like boosts and so on, but either way, so that's pretty much my VC package. Alright, cool. Next up we got my CMake list. So this is kind of like the engine essentially. So add subdirectory engine. I have this engine library. It's its own CMake, right? It's basically add library Kodotaku engine. I have a GPU class and basically a window class here, and of course the target include directories, and it's linking to SDL3 and GLM publicly. Public means that also whoever links to my engine would also get access to SDL3 and GLM. And also we have target compile definition SDL main use callbacks because we're using the new SDL3 main callbacks that makes it so seamless to support all sorts of platforms and just kind of makes the app or game loop much more defined. Either way, so this is my includes. I got right now just a GPU so far. It's basically just takes a window, a compatible window, right? It just uses it to verify presentation support and basically verify compatibility with the surface. And here we just got a context. This basically loads all our Vulkan functions instead of like letting the driver dispatch, which can be slower. Of course I'm using Vulkan HPP RAI here, which is way nicer because like when this instance gets dropped, for example, it would get destroyed automatically. I don't have to really worry about that. Here I'm using VKRAI physical device, Q family index, device, and Q. Nothing fancy. I'm using std optional because I'm not initializing these values in the constructor using an initializer list, so I just had to use this std optional pretty much. Some people usually use unique ptr, but that one actually allocates memory for it, which is not needed here. So that's pretty much it for that. Now the window HPP here, it's basically just takes a title, it takes a string, right, reference, and then a GLM IVEC2 size. So I would usually here say like use string view, but I can't really use string view here because SDL would need like a C string, and string view can't guarantee for me that the title would be, or the string view would be like, would have or would be null terminated basically, right? So that wouldn't work out. That's why I'm just taking a string reference here. Here we got create surface, which just takes a VKRI instance, all right, and it gives me back a surface KHR. It uses like the SDL function under the hood for that. Other than that, we have get instance required extensions, which basically just returns a span of extensions, right? And support presentation takes an instance, a physical device, and a key family index, and it tells you if it does support or not. And here, of course, we have a void show. And a unique PTR, SDL window, decal type, SDL destroy window. Since we're using like a C API here, I'm basically wrapping SDL destroy window in a unique PTR so it gets destroyed automatically. Without me having to like define the deconstructor. And if you define the deconstructor, you have to also define the copy constructor, the copy assignment, and all like 5 methods basically, which kind of suck. And here is the little implementation so far, nothing fancy. So we just got like a make instance function, which just takes a context and required extensions, and it returns a new instance with vk vulkan API version 1.4 with the enabled extensions here. Other than that, we have a very simple select physical device. So we're basically having a new function here, support presentation, std bind front, window support presentation, std ref window, std ref instance. So basically this window support presentation takes in an instance, physical device, and key family index. So the instance here and the window is actually fixed. So what I've done here, I used bind front to basically fix up the window and fix up. You could also do this using lambdas, but this is way more readable for me, first of all. And second of all, there is some few extra things like, you know, correctness, const correctness, and so on that bind functions usually do well. This is kind of like called curing. This is kind of like functional programming essentially. Here, I would actually want to just like pass in a reference to a window, but if you just like use window like this, it wouldn't really work because it would give us a pointer, which is not what we want. We want a reference. Hello Dissy, welcome to the live stream. How's it going, man? If you guys have any questions, please let me know. I'm making this stream just so I can like answer your questions pretty much. All right, so this stdref basically takes this window and gives you back a reference, right? You're pro coding Vulkan. Not really. I'm really struggling with Vulkan. I'm really struggling with, like, I'm just trying my best to make it as simple as possible with modern extensions and so on, and like modern tooling. So like the thing is about C++, you know, coming from Rust, it's like the tooling, the libraries are so fragmented and like everything is everywhere, and I'm trying my best to kind of adapt here. Bro, why don't you use visuals? Are you talking about Visual Studio or Visual Studio Code? Yeah. So here we're going through all the physical devices and Visual Studio. Visual Studio kind of suck. I gave it a lot of chances before and it just really sucked for C++. Like, for example, especially its IntelliSense, first of all, and second of all, it doesn't have like CMake first class support. I mean, it does have it, but it's not like the main thing for Visual Studio essentially. Visual Studio have its own MS build basically. Here, C-Line gives me a lot of cool things. I mean, even in C-Line, I still have a lot of friction with it, but at least it's like the best I could find. Other than that, there's also Qt Creator IDE. And yeah. I want to be OS Dev. OS Dev, that's wild. That's another level that I haven't unlocked yet. But yeah, so we're going through every Q family here. We're using stdviews enumerate function to basically get the Q family from this guy and to also get a Q family index, which is cool. Now, if the Q flags actually have the required Q flags, like let's say we want graphics and compute, then this would be graphics and compute, and then we could check it out right here. And it should, of course, support the presentation to this physical device and Q family index. Without this bind front, we would have to like specify instance in window, which is fine, but this is kind of cleaner, right? And here we return a new physical device. So physical device Q family index. Otherwise, we return an std null opt, basically a null pointer. Sorry, not like basically an empty optional, right? Anyways, here we got GPU. So first of all, we choose our physical device. If not, we just throw an std runtime. Bro, OpenGL versus Vulkan, which is better? If you're just starting out, I really recommend just OpenGL. Save yourself the struggle. Like the thing is, both Vulkan and OpenGL have their own kind of pros and cons. So OpenGL is honestly the most sane option. Like I tried DirectX 12, DirectX 11. I tried all of them, right? And if you're really just starting out, please go with OpenGL. Don't make my mistake. But even for beginners, what I really love about Vulkan is that a lot of things make sense. Compared to Vulkan, right? Compared to OpenGL. And also the debugging is way better. It's like than OpenGL. I want to make my own game engine. Well, here we're making basically a game engine. You could either use Vulkan or you could use OpenGL or whatever. Pretty much here we're using Vulkan essentially. So here we're basically creating a physical device. As you can see here, we're taking the first element of the tuple, here the second element of the tuple, and the priority required extensions, we need the swap chain, and we're setting the key family index, setting the key in C++ pointer is hard. Not much. What you don't understand about it. A pointer is basically just like, instead of creating a whole new object or copying that object, you're just pointing to an existing object. So like for example, let's say you want a house, instead of like creating a whole another house by copying the house, you just like point to the existing house pretty much in memory, right? Can you explain your code if you don't mind? Which part exactly? I'm trying to explain it. But there's just a lot going on here. So Q in place. Here we're taking the first Q in that Q family index, in that Q family essentially, but yeah. So this is the GPU CPP, and here we got the window.cpp, which is SDL. It just wraps SDL pretty much. Here we got a simple SDL exception, which inherits from runtime error. Line 3045. I think you were talking about this guy. Line 30. Which line? Just tell me exactly which one. Alright, so here we got the window. The window takes a C string, right? And then a size.x. So like we're getting the x-axis of the IVEC2 and the y. Here we got the flags, SDL window Vulkan, SDL window hidden, and SDL window resizable, meaning that we want the window to be compatible with the Vulkan, and we want it to be hidden at first, and then of course resizable. And here we're just passing in destroyed window, so it basically, are you developing a game? You could say so. You could say so, because like here in my CMake, I have two things. I have the engine here in its own library in CMake list, as you can see. So we got like the engine, which is basically here. So it's its own library, add library, and it only contains these files, right? And then here I have an application that is using the engine. So basically to make a window using this engine, you just say window.inplace. If you want to make a Vulkan GPU, you just say GPU.inplace. Like you just create a GPU, give it the window you want to be compatible with, and you're done. And then you just show the window, and that's basically it. That's the init. And here you can handle events. So that's pretty much. What do you think about Windows Bootstrap or ERP? Windows Bootstrap. What is that? Windows Bootstrap. Bootstrap. Web development stuff. I haven't got a lot of experience in Windows development. Which Windows Bootstrap you're talking about? Windows Bootstrap or ERP? What ERP stands for? Either way, here we have the app, which basically just contains a window and a GPU. And right now when we run the app, we still have nothing crazy. It just basically shows a window here. It just like creates a window and creates the Vulkan device. But right now we're going to continue to actually render something into the screen. Pretty much. Alright, so yeah, I guess let's get started. Alright, so where to even start here? Let's see. Yeah, so right now we're going to need another class, I think, for the swap chain stuff. Bro, make a mini Minecraft. We could try that. I never did that though. It's actually pretty hard. It's not like that easy to make Minecraft, at least not optimized. Though we could try it out. But yeah. Alright, so first of all, let's just get something cleared into the screen. Alright, let's see. Where we even start here? Device and the queue. Support presentation. I'm not sure what was in the design. Let's see. So I'm pretty much done with the GPU. I'm done with the window. Yeah, now we need to create basically a render class. So let's go ahead and do that, right? So C++, like if you're coming from OpenGL, my GPU is basically an OpenGL context, right? And the window, well, it's the window, right? So let's create a render now, which would basically contain the actual surface of the window and the swap chain and some other crap, right? So let's go ahead and create a C++ class, and we're gonna call this a renderer. And let's go. So what's nice about this architecture is that like you can support multiple windows at the same time using one device, pretty much. So you would have like one renderer per window essentially, but like just one GPU. So yeah, though you could probably just use multiple GPUs if you want, but whatever. Anyways, so we're gonna add this to the Kodotaku engine here, and let's go. So the render HPP would go to the include, and the render CPP would stay here. All right, and here we could just say render.hpp. All right, so let's start. Hey bro, what's up? I was learning OpenGL, but I left in because of study purposes. By the way, Vulkan or OpenGL? OpenGL is easy. Can it compete with Vulkan graphics? Vulkan, of course, is like the best. But really, for any solo dev, especially if you're starting out, just go with OpenGL. Save yourself the hassle. If I could have, I would have gone back to OpenGL, honestly, to get more basics for myself, because I really struggled with Vulkan a lot. because I didn't had that much basics before with OpenGL. I just like gone straight to Vulkan, which was really rough. And the problem is, the big problem is, I can't really go back to OpenGL right now, because every time I go back to OpenGL, I remember that like the niceties of Vulkan, right? So like both have their own pros and cons when you're just learning out, but really just start out with OpenGL. Don't like overthink it. Don't like repeat my mistake. The Bootstrap program is the first code that runs when a system powers on, loading the OS. Oh, you mean the bootloader. So like the bootloader basically looks for some, I believe, looks for some address in memory, kind of. Actually, no, hold on. So like the computer, when it just boots up, it look up some address in memory, right? And that address in memory would basically be your bootloader. So like you basically I believe you fill out some bytes using assembly, and then you have your code that boots up your stuff, right? That like you have some assembly code that runs at the start of the computer. It's just hard coded basically, right? And there you could do all sorts of crazy stuff to bootstrap your OS. At least that's what I know about that one. But yeah. Either way, let's see what we got here. So our class renderer contains some few things. Can we connect to other platform? There is Discord. Discord.codeotaku.com. You can find me there. I'm pretty active there. Alright, so let's go with VKRAI surface kchar surface username codeotaku. Though you could just chat, I usually don't like answer like direct messages, because like there's a lot of spam. So you could just, you know, message me in the server directly. Swapchain kchar swapchain. Are you making a game? OpenGL is only for rendering. For example, I want to make FPS game. It's only rendered. The object does not do any logic. Up layer move in that thing. If you really just want to make a game, just go with the game engine pretty much. I recommend starting out with Unity, because they have a lot of tutorials and you'll have way easier time. Really don't overthink it. Then later on, if you really want to, you could go back to like Go.engine, for example, or go to Unreal Engine or whatever. But start off with Unity first. I did Unity 2 years, but I want to level up. Level up in what terms? Like, what exactly you didn't like about Unity, or what did you do in those 2 years? Hello, nobody sus. Welcome to the live stream. I'm pretty much just making this live stream just to answer your questions, so please feel free. The Vulkan code is pretty much just mostly just filler and like my own little personal projects that I'm just using to learn more modern C++ idioms and how to architect a project. But yeah, I want to hold control on my game. Hold control of your game. I mean, yeah, you could do that. Like, you could go through it, but it's gonna be really rough. It's gonna be really, really rough. But yeah, you could do it pretty much. And for 3D, you really don't have that much options other than OpenGL, which is like the easiest option, which could allow you to do all things essentially. Like Blender, pretty much the whole Blender is in OpenGL. And most games like in the previous century were like in OpenGL. And a lot of it's still in OpenGL. So like you really, like even GTA 5, I think, is in like DirectX 11, which is kind of similar to OpenGL. So really you could do a lot with just OpenGL and DirectX 11. Most solo devs don't really need Vulkan, it's just too much. But of course, me being me, I like being, you know, on the bleeding edge. So I just gone straight to it, and I kind of regret it to some degree. If I were to start over learning Vulkan, I would start off just with OpenGL directly. Don't like overthink it. Just go with OpenGL. Where do you learn Vulkan? Just in and on, like on and off, pretty much. Just by myself. Usually, like you could find some Vulkan tutorials, but they're not that very useful for anything other than beginner level. And they're usually using some very old Vulkan stuff, like they're using Vulkan 1.0, and they cover some things that honestly, the best Vulkan tutorial I could like currently recommend is probably the Vulkan guide. Because the thing is, most tutorials you'll find about Vulkan, they cover some things that you really don't care about. Like, I mean, I understand, like most tutorials try to like give you the basics and the safe stuff. But really, a lot of things you don't have to roll yourself. You could just use libraries and such. And you could use modern extensions and so on. I made several tutorials on Vulkan before. You could like see in my channel, and even right now I'm making a whole new one, right? But like every single one, like in fact you'll find a lot of Vulkan tutorials on my channel, but like every single one I develop myself, like, right? So I basically make it better in some way or another. For example, instead of using raw Vulkan C API, right now I'm using the Vulkan RAI version, right, which is way safer and more like C++ thingy, you know. But yeah, but I really recommend the Vulkan guide if you want to get started. It's the most complete I could, because even my tutorials on my channel, they're usually incomplete. I just like give up halfway on. Hopefully not this time, but yeah, I really recommend this tutorial. There's also a new one, I think, like docs Vulkan. Though honestly, for example, in this video, in my new live streams of Vulkan, I'm covering some things that even this like tutorial doesn't cover, like some new modern stuff that makes Vulkan less painful, right? Or more painless. Well, yeah. I also give up yeah, it's too much for beginners, really too much. And I'm trying my best to like basically Vulkan realize that, and they're making some new extensions. For example, let's say you want to set a uniform in a shader. What you would do in OpenGL, you know, you just call one function, usually set uniform, and you tell it which uniform you want to set, and boom, done. In Vulkan, no, you need the descriptor pool, you need the descriptor buffer, not buffers, descriptor, what is it called? Descriptor tables and so on. Yeah, you need a whole bunch of ceremony stuff that usually doesn't even matter for modern hardware, but it's there because like there's some old hardware that actually benefits from it, but you really shouldn't really care about that. And that's why Vulkan is so complex, so verbose, just because of that. But there is some new extensions, like for example the Bush descriptor extension, which I'm gonna use, which would make it way easier for me. Like it's as simple as OpenGL almost, using VKKHR push descriptor. Another thing, like you would have to create a render pass, and you would have to create frame buffers, and you have to create all sorts of crazy objects. But using, let's say, VKKHR dynamic rendering, you don't need all that. And I really don't know why a lot of tutorials don't really like, you know, adopt these extensions. They just usually stick to Vulkan 1.0, which is very painful. And even if you're advanced, it's still very painful because you're having to manage the lifetimes and all these crazy objects like render pass and so on that doesn't even matter in modern hardware. How different is SDL3 GPU from Vulkan? No, you actually use both. And I heard you did see, I'll see the request later on after the stream. Either way, nobody saw. So SDL3 GPU is basically helps you to create a window. So here in my engine, I have a window class, which basically uses SDL to create a window, right? So if you see the implementation of window here, right, we're creating a window that supports Vulkan. As you can see, that is hidden by default and resizable. And that's basically what SDL3 I'm using it for currently. I'm also using SDL to create my cross-platform Vulkan surface. And I'm using it to get the instance extension. So in Vulkan, basically, you don't give it like an SDL window directly. Like you give it a native window, like for example on Windows you have HWND from Win32 API. On Linux you have XCB or Wayland surface and so on. So basically SDL handles all that cross-platform Vulkan, Windows stuff for you, so you don't have to, and that's what I'm using it here for. And yeah, that's pretty much what SDL is used for. SDL is also used for input. Like if you see in my application here, in my main function, I have these callbacks that SDL calls for me. App init would call it like when the application starts, and app event it would call every time the user did something, like, you know, click the mouse, click the controller button or whatever, or moved his mouse, or the window got resized, or anything, this SDL app event gets called. And here I'm basically deferring the logic to my application class event function. Here the iterate would get called every single frame. So basically SDL3, what it gives you input, like even controllers, like even Go.Engine is actually using SDL3 controller API to, you know, supports all sorts of controllers. Steam basically uses SDL2, and all sorts of I think Unreal Engine probably uses SDL2. I think so, yeah. And this gets called when the application quits. And then here in my application I actually have some logic that basically handle that. So here's the event stuff. Right now I only handle the event quit. When the user clicks the X button of the window, we want to just return, like, you know, exit the application with the success code. Otherwise, if there's some other event, then I don't care about it, just continue on the application. And that's pretty much what we have here. On the initialize, we're just creating a window and we're creating a GPU. And after we're done with the loading stuff, we're showing the window. That's basically it. Can't you use GFW? You could use GFW, and a lot of people use GFW, but GFW is less, you know, powerful than SDL. It only supports desktop. It doesn't have as much mature controller support, and it doesn't have, I believe, audio. It doesn't have all sorts of things, right? So SDL is like the most complete package for cross-platform windowing and cross-platform abstraction. So like instead of having to care about, you know, basically GFW only handles the windowing part for you in terms of multiple operating systems, right? But SDL like handles a lot more than like windowing. It handles controllers, it handles even threads if you really want to, and all sorts of crazy things. In fact, you could even make it, you like do dialogues, for example, or Lloyd DLLs for you in a cross-platform way that works on all operating systems. Otherwise, without SDL, you'll have to make sure that you uses several libraries for every single operating system, basically. Is Vulkan really powerful than OpenGL? Yes, but if you're really good at Vulkan. Otherwise, you could make some Vulkan code that is way worse than OpenGL. Right? So the thing is about OpenGL is that most of the code is in the driver. Like most of the code you would write in Vulkan, in OpenGL, the driver handles for you, right? But in Vulkan, the driver is way less code, right? So you handle more of, like, basically in Vulkan, you handle a lot of what OpenGL was doing in the driver for you, basically. And so since the OpenGL driver didn't know much about what you were doing in your application, it just have to guess a lot of things for you, which most of the time it works fine, but a lot of times, especially if you're doing some advanced stuff, it doesn't guess right, and so you get a performance hit, like you get some stutter in the game or something. But usually I would say for like solo devs, OpenGL is more than enough. It's really more than enough. Can we create COD level graphics with... you could even do that in OpenGL. You could do that in OpenGL too. It's not really about the graphics, it's just about the performance mostly. I mean, there's some few things that like new in Vulkan, like mesh shaders and all sorts of stuff that allows you to like push in some more efficient graphics so you could, you know, do better things. But like, unless if you're in real engine, like most of the time you don't even really exploit that very well. I would say probably most Vulkan code of beginners is way slower than OpenGL code. So yeah. So Vulkan is really gonna give you what you need if you really know how to use it, right? But that's basic. And if you use it for multi-threading, so basically OpenGL only exploited one core, right? But modern CPUs usually have, like for example, for me, I have 6 cores, right? And 12 logical cores. So all of those are wasted, or they could be used for physics or other things. But like the rendering is only one thread, basically, in OpenGL. I mean, you could even in OpenGL do multiple threads, but it kind of suck. It's not as good. In Vulkan, it's like from day one, it's designed for that. And like OpenGL is more like a state machine, or like you tell it, I want to use this now, bind this for me please, and then bind that, and so on. But in Vulkan, no, like you just specify everything you want, like objects. It's more object oriented kind of. Bro, please explain classes. Classes are not really much. They're just like, you know, a container of data, right? So for example, this GPU bundles all this data for me. It bundles the Vulkan context, the instance, the physical device, the key family index, the device, the key, like all the state of this GPU is right here. And it has some functions that use these data, these objects basically here. And that's all it is, really. That's pretty much it. That's what a class is. It's really not that hard. But yeah, so let's go back to our renderer here. So we're gonna have, for every window, we're gonna have a surface, we're gonna have a swap chain, and we're gonna have some few other things. But let's first of all, I guess, handle this. So let's go. All right, so how are we gonna do this? Well, first of all, we need a constructor, renderer. And so what this renderer would take, what it needs to function, it needs a window, first of all, and it also needs a GPU to create Vulkan objects for the renderer. So basically this what it would need is a GPU. So GPU, we're gonna take a reference here. Instead of taking like the whole GPU copy, which wouldn't work, we take a reference. We just point to an existing GPU. We don't create a new one, a new copy. Then we have like a window, and that's basically it. So we just create a GPU class and a window class, and now the renderer would use both of these classes to render into the screen, to render to this particular window using this particular GPU. And that's basically it. Now what I'm gonna do in C-line, I have this generate code that really makes my life way easier. I could say definitions, and there you go. And it just generates all the definitions for me for the header. Cool. Now let's basically initialize surface. Well, what the heck? Let's say, so how are we gonna do this? Well, we're gonna use the window to create the surface, the Vulkan surface, because like, you know, SDL that handles this stuff for us in a cross-platform manner. And here we need the instance though, but the instance is inside the GPU. So let's access the GPU instance here. But as you can see, it wouldn't work because the member is inaccessible. Bro, I want explanation for private and public, please, bro. Public, basically here the GPU can't access, like the renderer can't access the GPU instance, which I actually need here to create the surface. So I'm gonna basically either make it public so anybody could actually use the instance, or make it a friend. Hey, should I use VS Code or C-Line? Should I use VS Code or C? If it's C++, just use C-Line. Really don't overthink it. I tried all the IDEs. I tried even NeoVim, and while they all have like their own pros and cons, but generally C-Line is like the best you could find for C++. So yeah. Now here we can't access the instance. How are we gonna do this? So we either make, you know, the GPU a friend. So like friend class GPU. Wait. Not here actually. I think, wait, let me, if we do it like this, would it work? Not really, as you can see. So we should actually do it in the GPU class itself. Like we should basically declare the renderer to be a friend. I think like that. Right. Let's see if that would work. And yeah, right now after declaring it, it actually works. We can actually access the private members of it. And that's basically it. What does friend mean? So basically in our GPU here, we have a private variable called instance, right? We're basically hiding it from the whole program, right? To basically force users of our class to use the functions of the class instead of like tampering with our data, with our internal data. So here I made it friend so that the private variables here would be accessible from the renderer, right? So it's like, you know, a friend. You could basically borrow them your stuff, your private stuff. Like you could tell them about your private stuff, but otherwise someone else you wouldn't. So here we're declaring renderer a friend of GPU. Though this is one solution. A lot of times you would find like a lot of solutions. Here we actually can say, instead we could make the GPU itself handle this stuff. Handle creating the surface. So we're gonna say vkrai surface khr create surface. Or wait, what are we doing here? Yeah, pretty much. So we're gonna take a window and we're gonna say window.create surface instance. So here the GPU itself could access all of its private data. So we don't have to make anybody a friend, but everybody could make a surface without knowing about the internals of how GPU works under the hood. Also, what does that explicit mean? Explicit kind of hard to explain, but just like every time you have one parameter in your constructor, you better use explicit. It just kind of saves you from some implicit conversions. So like, what does that mean? vint32t. It's just kind of like an integer, pretty much. It's just an integer, but yeah. All right, so let's use this create surface function right now. Let's go back to our renderer here. Well, here. And now instead of doing this, we're just gonna say GPU create surface. Create surface, and then we give it the window, and it would create the surface for us. Next step we're gonna need is the actual swap chain. So we're gonna need the same thing for the swap chain here for our GPU. So basically our GPU would handle all the instance and device stuff in one place. Are you using MinGUI compiler? No, I'm using Clang because Clang is like the most cross-platform. It could be used on Windows, it could be used on Linux, it could be used everywhere. While MSVC could only be used in Microsoft, in Windows, and the GCC, it can only be used in Linux. Though there is MinGW, which basically makes GCC like available in Windows, but it kind of sucks. I mean, it's usable, but it really sucks, right? So if you're on Windows, just bite the bullet and use MSVC. Really, you don't have that much. There's just a lot of pain to use GCC on Windows. Pretty much, but Clang works on both. It works on Windows fine, and it works on Linux. and they have way more optimizations a lot of times because it's dependent on LLVM, right? And even my IDE actually uses something called ClangD, which is based on the same code that Clang is based on, which is LLVM. So that's pretty much it. All right. So here, what we're gonna do, we're gonna need to create a swap chain. KHR, create swap chain. And so how are we gonna do this? Well, Visual Studio is fine. I'm not saying it doesn't work. I'm just saying the best, in my opinion, is C-Line. And it's free, for non-commercial use at least. All right, so how are we gonna create this swap chain? So we're gonna basically say this, and the first thing we're gonna need is the device, right? The device, and after that we're gonna need the VKRAI swap chain KHR. Well, actually swap chain create info, I think. Wait, no. Swap chain create info like this, yeah. KHR. And we're gonna basically return this, and of course the device. And there you go, perfect. Now we're just gonna set a few things. But wait, we do need the surface though. Interesting. Let's see. So basically this guy needs a surface. So we're gonna basically grab the surface pretty much. So VKRAI surface KHR surface. And honestly, at that point, do we even need the window? Not really. We just need the surface, I believe. Explain swap chain create info. It's just like a struct containing some information that we're gonna set here to create the window. To create the swap chain. Either way, set surface, and that's basically it. Next up, we're gonna set clip to true. We're gonna set what else? Set the image format. For now, we're just gonna hard code the image format. So basically, you could set which image format to render to. And let's see, VK format. And I'm just gonna go right now with what the heck? We're gonna go with sRGB if possible. Let's see. R8, G8, B8, sRGB. Bro, what is tour project for? This is kind of like more like complex. Essentially, this is a very complex project. It's like basically Vulkan, so you have to know a lot else before you can understand this basically. But yeah, if you have some like C++ generic stuff, or just want to know some generic information about, like, if you need some advice on something, then let me know. Alright, so sRGB nonlinear. I think this is just 0, so you could probably it's just 0, fine. What else? So set image array layers. Pretty much we're just gonna go with one. Set image type? Oh no. Set image what? Array layers, color space, extension, mode, usage. For usage, right now we're just gonna basically clear that screen, or I mean, you could just render directly, honestly. No, let's just start with transfer DST, because we're just gonna clear the screen at first. What else? I'm gonna set the image format. Not really. What else we need is set image extend pretty much. So here the size of the image. So we're basically gonna need the size. So let's grab the size. So this is would basically be extend 2D dot set width. And here we're gonna basically say size dot width and dot set height, size dot height. And here we're basically gonna say GLMI vic2 size pretty much, yeah. Though actually we can't say width, we could say 0 and size 1. There you go. Alright, that seems to be great. Next up, set minimum image count. So here we're gonna need like the actual surface. Oh boy. But for the surface we're gonna need some extra things. We're gonna need the capabilities. Does the surface gives us maybe the physical device by any chance? It doesn't really. It can only give us the instance, so we're gonna need that too. So let's grab an KHR surface. But actually wait, we could just grab this. Well, we're already in the oh, I forgot. We're already in the GPU, so we could just grab, wait, no. Yeah, we could just grab the physical device, yep. Alright, so let's go ahead and do that. So, surface capabilities. This is what's nice about like bundling data together instead of like, you know, passing every single argument to the function. You know, it could just bundle it up together and it just works. So get surface capabilities, and there you go. Now we could use this surface capabilities to get some stuff. +1, and what else we gonna need here? We could use set alt swap chain. I'm not gonna bother with that right now. I think, yeah, that's probably it. The other stuff is optional, I believe. Yeah, I think so. And that's basically how you create a swap chain. It's really that simple. Though I would also want to honestly create the images and the views too. So how I'm gonna do that while we're at it? Let's see. So first of all, we're gonna create the swap chain here. Right, so this is basically VKREI swap chain KHR swap chain. There you go. And we're gonna return swap chain. I kind of hate the spell checking. I thought I disabled it, but it's still, oh my god. All right. Anyways, let's grab not right now the images of the swap chain. The thing is, this is not like a Vulkan tutorial exactly. That's why this seems so complex. I'm not trying to explain everything because it's just too much like to explain. Mostly making this stream just show you how to like structure a C++ project, some modern C++ idioms, and if you guys have any like generic programming questions, pretty much. This is just like a live coding session. But I'm not gonna explain every bit of the like the program is still, we're still preparing the first things that we're gonna need to run the program, pretty much. So that's the images, and so this would basically return an std pair of swap chain KHR and its images. Well, vk image, I think. Right now what we could do is we could return two things, a pair. Could return a swap chain and we could return the images. Now the swap chain needs to be moved. Otherwise, it would either be copied and it would get destroyed, which gonna suck. It's actually not even possible in this case, but anyways. So we're moving the swap chain and then we're giving back the user the images too. We should also honestly make the image views, I believe. How are we gonna do that? Let's see. Let's see. Or honestly, maybe we should just make this into a struct instead. Yeah, let's make it a struct instead. That's gonna be better probably for our sanity. Struct swap chain. Swap chain and its images. Right. And that's basically it. Otherwise, we could also say auto. We could use auto here and just say this. Right. Same thing here. Auto. And this. Or you could use just some IDE stuff. But anyways. So right now, how are we gonna do this? So we're done with this part. Now let's go back to the render part, I think. Swap chain, GPU, create swap chain. Though our swap chain here would contain actually a generic swap chain. And yeah, there you go. Now to create the swap chain, it needs some few things. It needs the surface and the size. And what the heck we're doing here? No, it needs to be this way. All right, cool. And here we need to give it the size. We could grab it from the window. You could say window.getSize. Now, of course, we don't have a getSize function in our window, so let's implement that. Let's go back to the window. And let's see what we're gonna do here. So instead, like show here, we're just gonna have ivec2. So glm ivec2 getSize, and then we're gonna implement this, and we're gonna return. So basically, we're gonna use SDL get window size here in pixels. Oh yeah, in pixels, because there's some high DPI stuff essentially. But how are we gonna do this? Support presentation. We're just checking if we can basically, if that particular physical device could like present to the screen, could draw into the screen, to the current display. Alright, let's see what we got here. So this could return basically an error. So if not SDL, then we're just gonna basically throw an SDL exception here. Failed to get the window size. Otherwise, we're gonna grab a width and a height here, I believe, and of course we're gonna use a reference here, height. So as you can see here, we're using references because it's gonna put the data there instead of creating a new one. So function has 3 parameters. Yeah, we're gonna need the window dot get, and there we go. So we tell SDL which window we're talking about. Then we tell it where to put our width and the height. And there you go. Now SDL will tell us the window size, and then we could return it to the user as a glm ivec2. Whoops. All right, cool. Yeah, you could check my channel. You could find my tutorials on Vulkan before. There's a lot of them. Just check the live streams or check the videos. There's a whole bunch of ones. Try to maybe look up the latest one or something. Or yeah, just choose one and watch it. There's some few people that told me that my earliest tutorial about C with Vulkan with GFW was the best. So I mean, I wasn't using some fancy extensions back then. which makes the job easier, but people said that like it was more helpful. I don't know. Alright, so now we implemented this. Great. Let's go back to our renderer. So now if we actually run this, we're probably creating the swap chain and creating the surface of the window. So as you can see, the window is here, but it doesn't show up yet because we're not rendering. Though what we could do though is we could say terminal and grab wiki-config GUI, no, and any running Vulkan executable, and then we can say API dump layer. And now we're gonna see all the Vulkan functions that are running. Oh yeah, I think we're not making a render just yet. Yep, we're not making a render just yet. So let's go to our application, and after our GPU, we're gonna have our render. So this is the optional render. Now, of course, we need to include this. And now we could go basically to here, and after creating the GPU, before showing the window, we're gonna create a render. There you go. And what's happening here is I always forget to set that to public, right? Yep, I did. And yeah, now this should work, I think. Isn't it? Yep, there you go, it works. Now let's see if that calls the Vulkan functions that we need, and does it succeed? And there you go. So we're calling the wiki create swap chain with success. 3 images. We're getting the swap chain images, and we're getting the swap chain images again. Once to get the count, and the other to get the. But like the Vulkan HPP RAI stuff actually handles that detail for us. But yeah. Either way, we're creating the swap chain now. Great. Great. Now, I do want to verify the design of this real quick. I really get lost in all these files. Honestly, that's too much. Crazy. Anyways, so where we're creating that thing, hold on. Yeah, we're creating it here. So we basically have a wiki array swap chain and a vector of wiki images and so on. Should we create it into its own class? Yeah, I think so. Probably better off to do that. Like you would create a new class for swap chain, which would hold all the swap chain stuff. Alright, let's go. Well, we should call a swap chain like this. And Kodachaku engine, Kodachaku app. Alright, let's just do this, and let's put the swap chain HPP here, and we're good. Thanks, Desi. Alright, so how are we gonna do this? So let's just go back to our renderer, I think. No, our renderer. No, GPU CPP. Where the heck is that class? Oh my god. Oh my god. I'm lost in my code. Seriously. There you go. Where is it? In GPU HPP apparently. Alright, let's take this and let's put it into swap chain HPP here. And of course this would be a class, and we're gonna need like include Vulkan / Vulkan HPP RAI. Okay, cool. Now this would basically, I guess, be private maybe. And there you go. And of course it's gonna have like a constructor essentially. And now we could move our GPU logic Like, let's include swap chain HPP here. And let's see what we got. So from here, we're just gonna need the surface and the size and the physical device. So this whole thing would be actually in the constructor pretty much. So let's go ahead and do that. Public swap chain. And let's just generate a definition here. And let's put this stuff. So as you can see, we're gonna need the physical device, the surface, and so on. And here, what we're gonna need: set width, size. All right, so first of all, we're gonna need VKRAI. I think the physical device, right? Or the device, or what? I'm so confused right now. Let's try the device. What we could get out from the device. Actually, I think the surface could probably give us this. Wait. No. You can't get them, right? How about the surface? Honestly, let's just do it. Let's just do it. Fine. So the device, and we're gonna need the surface gauge R, and we're gonna need the physical device. Let's go. Well, of course, this should be a reference. And of course, we're gonna need the size. So GLMI VEX size. Whoops. And there you go. But now we can't actually. You know what? Honestly, that kind of suck. Yeah. I think I'm gonna keep it as a create function. Starting an engine. Hello, Adam Rushford. How are you doing this morning? I'm pretty good, thanks. Welcome to the live stream. Yep, pretty much an engine. Once again. Let's see. Just for fun, pretty much. Nothing crazy. Yeah, honestly, I don't think I'm gonna go with this design. I think... Yeah. Yeah, let's just keep this stuff here, I believe. Maybe? Fine, let's just go with this. Fine. Almond Engine, welcome to the live stream. So set surface, and I think that's basically it. And then, now the nice thing about that, fine. I really hate initializers in C++, honestly. Let's make them an optional. Right. Let's make them an optional. And then we could basically say swap chain. Like, I need to basically use that freaking optional everywhere. Right, so swap chain dot in place. Right, dot in place, and now I could remove this stuff and do it like this. All right. Now I have to basically use this now. Get images. Right. But actually I should use this. And in fact, I'm gonna make sure to do it this way and this way. And yeah. All right, we gotta change it here too. And now once we're done with this, but of course I gotta update this. You need to keep the core functional or low overhead at least. Yeah, definitely. So physical device, the device, and the surface and the size. Now here in the GPU function, it's gonna return the physical device, the device, the surface, the size. All right, cool. And that's basically how it goes. So we abstracted away the swap chain. That seems good. Want a cheat code? Sure. Just use OpenGL. That's the cheat code. Alright, so there we go. Perfect. Now let's go back to where we were. Google Ultimate Functional Vulkan. Ultimate Functional Vulkan, huh? Where is it? Can you give the link? No, I can't find it. Not really. Maybe this. Right. This one? Or I should search for it. Where's the repos? Here. Ultimate Vulkan. Which one? This one? Is it using Vulkan HPP though? Oh, you're using that's good. You're using GFW though. I'm using SDL. CMake lists. Oh, I see. I'm just using C-line regular. Let's see. Where's the actual code? I'm already doing that, fine. I seem to be using Visual Studio though, VSCX project, so it's not really cross-platform. Where's the code? I still can't find the main function. Where is it? Yeah, I don't know. My design is very opinionated. I'm using like Vulkan HPP. I'm using VC package. I'm using SDL, GLM, everything C-line. I'm doing all sorts of crazy stuff. I have like 2 CMake lists. I have one for the engine and stuff so on. But yeah. Either way, let's continue. Where I was. So after creating the swap chain, what do we need to do? Let's see. I think we need to create the frame resources. The frame resources. So we're going to create a new C++ class, and it's going to contain the frame resources. So yeah, okay. And it would basically contain some synchronization stuff. It's going to contain like it's a drop-in header only Vulkan texture. I can't find it. Like static. This. I'm not using GFW. I'm using Vulkan. I'm using SDL3 first of all, and second of all, I'm not using Vulkan HPP regular. I'm using RAI, which doesn't need the dispatcher stuff. It just handles that for me, and a lot of other things. What else? Clean up. I'm not doing the cleanup myself. RAI handles that for me too, because I'm using HPP RAI. What else? Just so I can give you some feedback on what is different. I mean, of course, this also works, but I'm just like, my design is very opinionated. I tend to really do things my own way. But yeah. But I really recommend using GFW. Is kind of fine as long as you're not like targeting other platforms other than desktop. Other than that, I really recommend using the Vulkan RAI stuff, because instead of like, you know, for example, destroying the instance, the Vulkan instance and the Vulkan objects, it just does that for you, and a lot of other things. Also, it handles the dispatch for you. So like every single device have its own dispatch table. So like a lot of application that uses the Vulkan C API or the HPP, the HPP one can't really make multiple devices because they're not handling multiple device dispatch tables. They're using globals, and that suck. Now, of course, usually you only want like one device, but if you ever need, for whichever reason, multiple devices, then it wouldn't work. I mean, you could make it work out, but it's like not the best way. But yeah, but like RAI just handles all that stuff for me. I don't have to really think about all of that. But yeah. Okay. Nobody's sus. Hey, can you help me with C-Line? What's your problem with C-Line? Alright, so let's go back to our business here. Let's see what we got. So the VKRAI, we got the semaphores, of course. The image available semaphore. Let's actually just include Vulkan HPP RAI. And we're gonna need the render finished semaphore and the in-flight fence. Perfect. Now GitHub Copilot start to pick up all my patterns here. That's great. I wrote my own multi-context engine, but only went so far with Vulkan yet. Yeah, it's very draining. I also gave up on a lot of Vulkan projects. It was just too much. But hopefully, like every time, I hope I could, like, you know, continue. But honestly, at this point, I'm just doing it as a recreation. But yeah, either way. So we got the class frame resource, and this is of course private. Now, and of course we're gonna have like public frame resources, which takes an instance. Yeah, actually, is it really an instance? I think probably device. I think we need the device here. So basically Vulkan requires it has no shared context is what I hear you saying. No, so no, that's not what I'm saying. So basically, if you call Vulkan functions directly, you're calling into the loader, and the driver has some overhead to point you to the right driver, right? Which suck. That's the first one. This is like the native, like the simplest way to just use the Vulkan loader directly, which suck. It adds some overhead. The second thing is using Vulk, or using the way you're doing it here, which is using, what is it called? Let me see. Oh my god. I can't find code to save my life. Yeah, there you go. So you're doing Vulkan HPP default dispatcher.init. There you go. And you're doing it here. I mean, this is fine. This is fine for what you're doing. But if you ever need, like, this is basically global, as you said, global function pointers. Now, if you ever need multiple instances and for whatever reason multiple devices, then you have to use dispatch tables instead. Now, in here, I'm not even needing to do any of this stuff, first of all, and second of all, it's not global. So like if you go to, well, let me see, where is it? If you go here, I got the context. The first object is the context. This basically loads the global Vulkan function pointers. If you see here, you're actually doing it from like a dynamic library. It's doing it for me, right? That's the first thing. Second thing, the instance RAI loads its own function pointers, dispatch table, right? So you could have all sorts of instances and it just works. You have its own table. And then the device itself also have its own dispatch table inside of here. So all of this is handled for me by Vulkan HPP RAI itself. Now, I'm not saying that your way is wrong. It's actually fine for what you're doing. You're making, you know, one instance and one device. But I just prefer personally this way of doing this things, which is way more flexible. But yeah. All right, so let's continue where we were. Yeah, not a lot of people know about this because most people only just use like Vulkan like the C API, or uses the Vulkan HPP regular API. I'm using the latest one, which is the RAI one, which basically destroys everything itself. It handles its own dispatch tables and so on. But yeah. All right, so I don't know how people can keep track of all this. Let's see. Honestly, this one I'm just gonna make a freaking like struct. Really, I don't want to bother with the constructors and optionals and so on. Really, yeah, let's just go with that. Honestly, at least for now. Yeah, I think so. Let's just go ahead and do that. Oh my god, this is what I hate about classes everywhere. It's really modular, but like, bruh, I tend to get lost. I don't know how people could like manage all these files. Yeah, pretty much. I'm blocked. Let's go back to our renderer here, I think. So after our swap chain, yeah, this is our swap chain. What are you drinking? I'm drinking coffee. My morning coffee. What's left over in there? No, like GFW is fine. Like a lot of samples uses GFW. It's just not like, it's just not the best out there, pretty much. If you really care about cross-platform, basically, and so on. But anyways, all right. So now let's make a grid array, essentially, array of frame resources. Now here we're gonna have like, let's say 2, fine. And we're gonna use that type, essentially. And, I don't know if I really want to keep this way. I don't know. Let's remove these. Let's remove these. Fine. Let's keep this simple, please. Let's go back to our renderer here. And what we're gonna do basically, where's our render HPB? Here we go. Okay. And instead of this, we're gonna say this. Alright, so we're just basically doing it here. Cool. So this should be our in-flight frame count. And this should be like, let's say, const x per flight frame count size t, right? Is equal to 2. Okay. Non-static data member, did you intend to make it static? Well, yeah, static. And then we could like make an array here. Now, how are we gonna do this? Image available semaphore. I think we probably want a CD optional again. Oh man. Oh man. Now let's go to our render and let's see what we're gonna do here. And we're gonna go basically through every frame resource in frame resources, right? So of course we're gonna take a reference here. And now what we're gonna do is we're gonna in place that. And here we're gonna construct all of that. Right, so VKRAI, I think the first one is like a semaphore, right? So here you need the device. Oh boy. Well, for that we're gonna need, yeah, I see. So let's go back to our GPU class, fine. And let's create a function called create semaphore and create fence. Create semaphore. And also while we're here, we're gonna create some other things too. create fence. And we're also gonna have a few other things like create command buffer, command pool, create command buffer, or actually allocate command buffers. Or maybe you don't need them because the command pool could do that for us. But at least we need these, I believe, right? I think you still need to allocate, yeah. Though here you would need like RAI command pool. I can't make up my mind on which naming conventions to go with. But who cares? We could refactor that stuff later. Alright. That's... Alright, let's implement these now. We're just going to say refactor, actually generate code, definitions, okay. And let's implement these real quick. Wait, what the heck? No. No, wait, stop it. That's Indo. Can you? No, you can't. IDEs. Alright, fine. Let's go back to our GPU HPP here. And we need to make sure that it have the right type. VKRAI semaphore here. Now here fence. Here command pool. And here it's going to be like a command buffers. Well, command buffers, not command buffer. And you probably also want the count though. So like UN32T count in some sense. Or just size T really. I hate mixing up types. Now we could like, so create command pool. Command pools actually needs, you know, god damn it, UN32T Q family index. Just use it, fine. Q family index, and what else? Create fence is fine, create semaphore is fine. Yep, right now let's just create this. So how are we gonna do it? Generate code, definitions, okay, boom. Now let's return here the device and the vacate semaphore create info. Wait, device like this, right? And the same thing here, create fence. Fence, create info. And same thing here for the command pool, kinda. Now, instead of this, we're gonna go with command pool create info. And here, we're just gonna go with command. Can we actually say allocate command buffers? I wonder. Wait, what the heck? What? Allocate? No. That doesn't make sense. Let's see how we can do this. Allocate. Does this return command? No, it doesn't. Huh. Oh, actually you just do the same exact thing, right? My bad. So I think you probably just like pass in the command pool and then pass in the vacate command buffer allocate info. Yeah, I forgot. Is that it? Come on. Or maybe the device actually. Yeah, probably. Yep, exactly, the device. Right. So let's see what we got here. This one, we don't need to change anything really. This one, we do need to change something. We're going to set the flags to vacate signaled. Yeah, it doesn't work that way. So fine. create flag bits, e-signaled exactly. And now here, command pool create info. We're gonna set the queue family index to queue family index. Though we also need some flags here though. So like command pool, create flag bits. So e-transient and e-reset command buffer. Transient, it kind of depends, but for now, let's just do it anyways. We could think about otherwise later on. Other than that, allocate command buffers. So set the command pool to our command pool. Well, what the heck? Command pool. And next up, we set the command buffer count to our count, or like command buffer count. Right. Whoops. There we go. Rename this parameter. Why? Fine. Fine. Okay. And that's pretty much it, I believe, for this one. So as you can see, the GPU basically handles all the creation crap for us, so we don't have to do it every single time. So it's really a lot of like effort at first, but later on we're gonna have a very clean API which handles all the freaking details for us, the boilerplate stuff. Either way, right now we could go back where? To our render, I think. Let's see, our render, where is it? Here we go. And render dot. Can we go from here to the actual implementation? Yes, we can. We could do this. Right. Perfect. So now frame resources in place. Now what we could do essentially is GPU create semaphore, and then GPU create semaphore and GPU create fence. And there you go. That's pretty much it. Lovely. And we don't really need this. And there you go. Perfect. And yeah. Now we created the frame resources. Is there anything else we're gonna need? Well, of course, we're gonna need to allocate the command buffers too. And for the command buffers, we're gonna also put them in there. Honestly, let me just close up all the other tabs right now. There we go. Oh yeah, actually when you, all right, cool. So here we're gonna add another thing, which is like the command buffer, I think. Or honestly, no. Wait, let me see. Should we do it that way or that way? Let's try this stuff up. So command buffer. So this is like your graphics command buffer. Because like you could have multiple of these. Right, perfect. So your graphics command buffer. Now what we're gonna do basically is, first of all, we're gonna allocate the command buffers. Actually, we need the command pool first. I forgot about that. But honestly, no. What we could do instead, we could have like one global command pool for now, I think. I mean, what you would usually do though, actually no. Because if you do that, you wouldn't be able to, let's say, create a render in a different thread. Yeah. So no, don't do that. We're gonna keep the command pool here in the renderer. So where are we gonna put it though? Where are we gonna put it? Let's put it here. Fine. So we're gonna say vkrai command pool, but of course we're gonna need that bloody optional again. And vkrai command pool. This is what really sucks about the RAI things, but yeah. Now, but the nice thing though is that once you get a command pool, you know it is valid. You're sure that it's not null PTR or some weird crap or invalid state, which is great. So yeah. All right, cool. So how are we gonna do this now? So we're gonna go back here and we're gonna say that graphics command pool dot in place GPU create command pool, and we pass it in here the key family index. Oh yeah. So can we grab the graphics key family index? Well, we have to. Yeah, we have to make it available from the GPU. Gotcha. So can we just like create this member function real quick? Yeah, perfect. Love that. All right, and then we could basically just say generate definition. Oh my god, look at that C-line. I just need to learn more about how to like make C-line like make me more productive. But yeah. So honestly, let's rename this to graphics key family index, because we could have multiple of these pretty much, and there you go. Now I think we're good, right? Yeah. So we're creating a command pool for graphics, and next step we could allocate the command buffers here. So command buffers, GPU allocate command buffers, and it would basically return for us an RAI command buffers. Now, let me see one thing real quick here about command buffers. So it's basically just a vector, though actually they're kind of like inheriting from vector, which is weird, because like you usually don't want to inherit from them, from like the standard containers. Though what it does give me exactly, does it like have some deconstructor that deallocate all of them, or it doesn't really seem like it's, yeah. All right, fine. So what I'm honestly gonna do here really is I'm just gonna move all the command buffers from there. And to do that, I need to kind of like zip the, right? So, cause like the frame resource is also in-flight frame count, yeah. Do we have zip in C++ yet? I wonder. I think we do. I could be wrong though. We do seem to have like a zip thing. Hold on a second. How does C++23 zip works? Well, range, well, views or view zip works. Let's see. Because like I'm coming from Rust, and I would just usually do that. I heard in my mind 2000 Microsoft would encourage people to drink some alcohol because it would increase productivity. I never drank alcohol in my life. I only drink coffee or tea, pretty much. Let's see. std view zip. Yeah, that's how you basically do it. All right, cool. Love that. So right now what we could do essentially is std views zip, I believe, though coffee is the best. Yeah. Let's see, include ranges. I mean, I'm really addicted to coffee. I wonder what would happen if I get addicted to alcohol, so I never touch it. Pretty much. So yeah. This is the way that I wanted, yeah. Though right now we basically want to say that like this is the frame resource and you get the command buffer too. Is that how it goes? I think so. There you go, cool. So we basically zip the frame resource with the command buffers, and then we could basically grab the command buffer here. Though it wouldn't accept it because we need to move it. It doesn't, it want to own it basically. Though, can we actually move it? That doesn't seem like it's want to work out though. I wonder why. It's probably something to do with zip. Probably. So it gives us a reference, but I want like to own it. Well, let's do something interesting to kind of isolate the problem here. We could say that command buffer here is equal to this. Can we? But of course, I gotta add that thing real quick. Redefinition. Whoops. So remove reference type. Yeah, I don't think this would work. Let's ask ChatGPT. It doesn't allow me to move the command buffer out of the vector. I only learned ownership with Rust. I don't understand how people in C++ learn ownership. But when I've gone back to C++, I kind of understood ownership from Rust. And like also very paranoid about like lifetimes and so on. Also really loving the Rust iterators, which are basically the new C++ ranges and views. You've got two things biting you. The zip yields a tuple of references, but your structured binding drops those references. You end up with copies in the binding, so just moves the copy, not the element in the vector. Alright, so what's the... Oh yeah, so you have to do it this way. Preserves the referenceness from zip. Okay. C++ is wild. Like really wild. Let's see if this works. Is that the way it's supposed to work? Huh. That doesn't seem to work though. No, that doesn't work. Yeah, that kind of suck. I'm probably better off to just, you know, not do the zip, because kind of like views, they're basically not... Or we could say CD exchange. Yeah, kind of like Rust. That's interesting. Kind of like Rust. Would it work though? Let me see. So if you say command buffer with that, would it work? Oh, actually I am getting the command buffer now. Though it's still not accepting it. What? That is weird. And of course that doesn't work, wouldn't work really. You know what, let's just go back into without zip. Cause that wouldn't work out. At least in this case, because we're mutating the command buffers, you know. So that makes sense. Yeah. So what we're gonna do instead, you know, just gonna do command buffers. Oops. I for the index. Right? But of course we're gonna need the I. Now here we could just use std views enumerate. Let's make sure to include ranges here. And now we're gonna grab I. Let's try that one. And of course we don't need this one now. Would this work? Though I think we still need to std move this. Right? Yeah, this works now. Perfect. Love that. Yeah, it's kind of weird, but there we go. And there we go. That's how you do it. And then we could just drop the command buffers, I think, fine. Let me verify with ChatGPT, why not? It's still trying to zip them, but that doesn't work, would it? I mean, if we do it... Actually does. What the heck? Really? Like, ChatGPT is wild. Like, really wild. Yeah. It works. Crazy. Now, this is cursed. This could blow up at any point, but if it works, don't touch it, I guess. Alright, fine. That's so good. So it basically made this into an R value, and then it moved it here. Wild. Alright, so that's so cool. That's so freaking cool. Alright. Okay, so where we're actually calling this stuff now. So this is the constructor of render. Let's make sure this is working just fine. Build failed. What the heck? Why? It probably effed up something. So let me just clear the cache and reload the project. Ah, I see. So it's still thinking that I have those files. Oh yeah. Alright, now. Well, let's reload CMake. Let's try again. There you go. So create fence, create semaphore, create fence. Allocate command buffers, there we go. Everything working fine. Perfect. So that's great. That's great. Now what are we gonna do next? So we have all the frame resources we need. We have the graphics command pool, we have the command buffer, we have the swap chain, we have the surface. So I think right now we could just, you know, start really rendering stuff into the screen, isn't it? Yeah, probably. So let's go to the swap chain because we need to prepare some functions like acquire image, essentially. So this would basically give you a... let's see what we're gonna do about that. Should we return just an index or should we return a vacay image directly? I think I'm just gonna return a vacay image directly, honestly. I believe, yeah. So, fine. So, wait. We could use auto here. Auto, then vacay image. There you go. Perfect. Now the thing is, it could fail of acquiring image, but for now we're just gonna ignore that for now. And then we also gotta need present image. And okay, so how are we gonna basically design this though? The thing is about present image, you actually give it the index of the image to present, which kind of sucks. Now we could either just go with the index anyways, or we could just save the currently acquired image index. Yeah, I think that's what I'm gonna do, honestly. So you just, you know, say present image maybe, and then it just presents it for you. All right, fine. Let's say you enter the to image index. There we go. And yeah, so acquire image, and then it gives you vk image, then you present the image. Is there anything else we need here? I don't think so. Yeah, that's pretty much it, I believe. So well, swap chain, aren't we gonna need the GPU though? Actually true, why we're not taking the GPU here? Does that work? No, it wouldn't. Can you that's pretty interesting stuff. That's some pretty weird stuff. Should we make like the swap chain a friend of the GPU and access its variables, or? I think probably the easiest choice right now. Yeah, let's do it actually in the GPU, or save the GPU as a reference. You know what? Let's save the GPU as a reference, I think. Right, so after we save that, we could probably, instead of this whole business right here, we could just take the GPU. And that's way better. Now we do gotta change the stuff a bit here though. Yikes. Now the problem is we're gonna need to well. Well. Honestly, I think I'm gonna go with the create function. Yep, probably. Yeah. What I'm thinking basically is that this business should really be in the GPU, in here, in create swap chain essentially. Yeah, probably that's what you want. And like you would have VKRAI swap chain KHR, swap chain, and here the device, right? Now after creating the swap chain, and here of course your physical device, and whoops, we gotta do it now like this. And here you probably want to unwrap the optional. Yep. And the swap chain would just kind of like be a wrapper around this. So it would basically contain the GPU itself, which is basically this, and the swap chain. Right. Though I think probably maybe this, I don't know. So let's go back to the swap chain here. So it's taking a GPU and a size. Do we even need a size here? I don't think so anymore. We just need like the actual swap chain handle. Swap chain. Whoops. And honestly, right now we could remove that optional here in this case. And we could just say swap chain, add std move, and there you go. And let's also initialize GPU. And yeah, let's make sure to initialize, I guess, GPU first. Why not? And we're good. So I'm pretty much just kind of using Vulkan as like my playground for architecture, like project architecture and so on. But yeah, so we got the GPU and we got the swap chain, cool. And now here we could set the images to swap chain get images. What the heck? There we go. And that's basically it, I believe. So the GPU basically creates those stuff for you. And now I think we could just say this maybe? Or how does that work? Well, we actually need to move this into that class. We move ownership. There we go. Well, actually no, it doesn't work. What the heck? Why? You know what? Can't we just do it like this? Can't we? We do need a CD move at least. All right. All right, this works. No, actually it doesn't. What the fuck? No matching construct virtualization swap chain. Why? Error, in known type name GPU. What the heck? Requires one argument. Oh, I think I know exactly what's wrong here. So if we go to the swap chain, CPP, yeah, there we go. So yeah, we forgot about that part. So actually the implementation should be here. My bad. So let's go back to the swap chain H file. Where's the H file? There we go. So this shouldn't be here really. Should just have the declaration, yeah. I forgot completely. And then here we got the implementation, of course. And there you go. Now if we go back to the GPU, and also, of course, we shouldn't put this here either. We should generate definition here. Wait, what the heck? Well, this should return BKRAI swap chain KHR. And let's see. Actually, I'm so confused. Actually, no, swap chain, yeah. Swap chain, and then Yeah, right now it works. Okay. So, well, still it doesn't. What? Oh my god. So let's verify step by step here. So we got the create swap chain function, right? It takes a surface KHR and a size, and it returns a swap chain. Now in the GPU CPP, it's the same thing, right? So surface and size, and it returns a swap chain. Perfect. Now the problem is maybe the swap chain. So swap chain takes a GPU and it takes a swap chain here, right? And yeah, that seems about right. So probably something to do with this. I don't know. What if we just return this? I don't know why. All right, let's see the error. Let's see the error. Known type name. Something is wrong with the LSP. So let me just, yeah, it really sucks when that happens. The IDE gets broken. It's really annoying when that happens. Still analyzing. Oh boy. At this point, I'm so... Let me see if we could figure this out. Because the IDE doesn't show me that like GPU is not. What the heck? Like the IDE shows me something and like the compiler shows me something else. Which is really annoying. Ah, circular dependency freak. Okay. Okay. Circular dependency. Oh my god. Okay, gotcha. In the swap chain, we just need a forward declaration. Yep. So this was what was causing the whole freaking problem, a circular dependency. So like the GPU is like, oh my god, that was wild. Really wild. Okay, so now this works, I guess. Yeah. So, I mean, I knew about circular dependencies, but I didn't pay attention here. Oh my god. Because, like, you know, the swap chain was dependent on the GPU, but the GPU was dependent on the swap chain. Oh my god, dude. Crazy. And yeah, we're back into business. Well, that was wild. That was wild. Really, really wild. Alright, fine. Let's go back now to what we had. So, what we're even doing. Let's see. So we got the surface, this function. Oh yeah, we were wanting to make functions for. Now we could actually do that, yeah. So let's actually start by the GPU, I think. So for the GPU, what we're gonna do? So you're basically gonna need a way to acquire an image using the swap chain. So like swap chain, and then of course present an image. Sorry, present swap chain, or just like, yeah. I mean, yeah, it's fine, I guess. Is that it? Well, here we do need the image index. What's a good place to learn about Vulkan objects like swap chain and semaphores? Vulkan API is usually verbose compared to OpenGL. You could either watch my previous tutorials, my video tutorials, but they're mostly incomplete. I'd recommend there's the Vulkan guide. This one gets straight to the point. It like ignores some few things. And like, because there's a lot of things like you shouldn't really care about. It's just like the first time setup. A lot of the things right now that I'm doing is just kind of like the first time setup. But after that, it's kind of gonna be like a smooth sailing, right? Especially that I'm like doing abstractions and so on. Either way, there's this Vulkan guide. There's also Vulkan tutorial. Though this one is very verbose, but a lot of beginners find it helpful. But this one is more modern. It uses some libraries to ignore some things. Like for example, it uses something called vk bootstrap library, which simplifies the creation of swap chain and so on, but I didn't want to use it because I'm using Vulkan HPP RAI, which doesn't work out well. Other than that, there's also a new tutorial that I haven't tried myself that is trying to also use some modern Vulkan stuff. So if you go to the Vulkan documentation, docs, I think this is probably the official one, though it didn't have a Vulkan tutorial before, but if you go here, there we go. So dynamic rendering. Render passes is even more verbose and really suck. So always use dynamic rendering for modern renderers. So yeah, and Vulkan HPP if you're in C++. Though they're using modules, C++ modules, I never got C++ modules to work for some reason. But other than that, yeah, try and see which one you like. I'd maybe suggest starting maybe with this one, try it out. It's the newest of them all. If that doesn't work, then go with this one, the Vulkan guide. Otherwise, go with this one. It has some really old practices, but it works. This is the first tutorial that I kind of followed. But yeah, that's basically it. There isn't really that much resources, but well, anyways. Alright, so what else? Here we got the present image and UN32T image index. If you got any other questions, please let me know. Alright, so acquire image. Now here what we're gonna do, we're gonna say device acquire next image to KHR, huh? Where is the weird? There's only next image 2. Weird. Maybe it's actually inside of. If we go here, right? Let me see what kind of methods we have here first of all. Yeah, we do have a acquire next image function apparently. Oh, so you're telling me I didn't even need to store the device myself. Freak, so this whole freaking refactor. Oh my god, dude. HPP already handles that for me, apparently. So that's so sick. That's so sick. How about presentation? Does it handle that? No, it doesn't. So, but the acquire image, it does. Okay, fine. So, how are we gonna go about that? Then, all right. So let's remove this from here actually. Let's go straight to the swap chain right now, and let's just say that we're gonna have acquire image. And it's just gonna return a freaking vk image, I think. You're gonna see about that. Whoops. Well, actually, let's go with auto really, and then vk image. Let's see what we're gonna need from there. We're probably gonna need some vk semaphore though. So like acquired image acquired semaphore, I think. Image acquired semaphore. And we shouldn't implement it here, of course. Let's just implement this. And let's see what we got. So swap chain, the acquire next image, and here we give it the timeout, which is like std. I can never remember this stuff. Numeric limits. Yep, there you go. There you go. We're just gonna not bother with the. Wait, what? Hold on a second. Actually, no. It gives us the result in the UN32. Okay. So auto the result, comma, the image index. So for the image index, we're gonna store it. So how are we gonna store it? Well, this way. Next up, we're gonna return the image in that image index. Right. But for the presentation though, we're gonna need the help of the GPU. So for the presentation, we're gonna have present, and you're basically gonna give, I guess the swap chain. I'm not sure. Let's just freaking implement it and see what it's gonna need. Pretty much. Like, dude, oh my god. Alright, so let's go with the device. And then let's try to present a swap chain. And I think I know why they did it this way. They didn't put the present function in the swap chain because like you could present multiple swap chains at once, pretty much. Maybe that's why they did that way. Yeah, probably. But why I can't present? What? I'm so confused right now. I'm pretty sure the swap chain itself doesn't have it though, right? Yeah, no, it doesn't. And so, which one have it? I'm confused. Or maybe it's not called... Oh yeah, I think... Wait, hold on. Let me just search it up. Let me look it up, really. So, swap chain KHR. I'm really losing my mind right now. Present Vulkan. So let's see how they doing, or maybe they submit the image or something. I can't believe I forgot. Let's see. Where is the call? Come on. As you can see, this tutorial really do a lot of stuff which is actually needed for like a production kind of thing, but like for tutorial, bruh, you don't need all these chicken and all this crap and anyways, where is it? Swap chain image views. There you go, render and presentation. Let's see where that happens. Come on. Oh yeah, Vicky Q. Oh my god, it's in the queue. I was like going crazy, man. So it's inside the queue. Okay, gotcha. Alright, so it's inside the queue. There we go. Oh my god. Alright. So sorry. Alright, let's see what we got here. So the swap chains, and here we give it like the swap chain essentially. And we're also gonna need like the image index in some sense. Right. So first thing first, you're gonna need like the swap chain KHR. And this would basically give us, I guess, the results. Yeah. All right, so swap chain, image index. And now we're just gonna make sure to have the right signature here. Yeah, and there we go. So now that we got that out of the way, now we can go back to our... I did see your previous Vulkan stream where you implemented the red window. Where to go from there? I'm gonna do whatever like here. So we're gonna basically make a triangle. Right now, I'm kind of making a new way of doing things. Like I'm basically kind of splitting things up, which is actually kind of challenging because like I'm not sure. I need to design kind of the API essentially. But we'll see. But like today I'm gonna cover, hopefully if we have time, gonna cover compiling shaders at runtime. using shaders, just like OpenGL basically. I'm definitely losing some brain cells here, so bear with me, please. All right. So set swap chains, set image indices. Yeah, we need to dereference that, I think. And is that it? Yeah, pretty much. All right, so now let's go to the swap chain.hpp, and then we're basically gonna have a present function here. Really that simple. And of course, it's probably not gonna return anything for now. And we're just gonna generate the definition. And here it's gonna be very simple. So we're gonna say GPU present, and then we could pass it our swap chain, and then we could pass it our current image index. And that's way nicer. Way nicer. Oh. Wait, what? Wait, do we have that freaking circular dependency again? Function presents the DS return, or maybe we just have to like do this. I don't know. Wait. Yeah, I mean we should be able to just pass it in there, but it's not working out. Cannot be used before it is defined. But it is defined here though. Yeah, this really sucks. I think we probably need to like make it a unique PTR possibly. I'm including the GPU header in the CPP file. Why it doesn't work? I think I probably need to use unique PTR for that. Let's see what ChatGPT would say. Oh, maybe I just forgot to define some weird thing. Oh yeah, I did. Oh my god. So was the whole problem all along? Are you kidding me right now, dude? Wait, let me see. The swap chain dot CPP. Oh. What if we do this? Would that work now? Yeah. So don't forget your types. Here's another vulkan of C++. Welcome to C++. Alright, so that's pretty much, I believe, it. Though we should probably return the results, honestly. Should we? Let's not handle that right now. Alright, so we're done with that part. So let's see what we could do. Now, let's go back to our render finally. And we're gonna have a render function, I think. Yeah, probably. A render function. And let's see how that would go. Let's generate the definition. And the first thing first, we're gonna acquire an image to render to. So how are we gonna do that? We're gonna take it from the swap chain. Acquire image. and we're gonna give it our well, first of all we need to actually grab the correct frame resource. So frame, right? And we're gonna say frame resources, though we're gonna need the frame index. So this is like in-flight frames. So how are we gonna do this? Well, render.hpp, where is it? Here we go. Now we're gonna need like a uint32t, maybe image index, or what? Or maybe size t in this case, honestly. Yeah, size t, fine. Well, actually not frame image index, frame index, because like you have image index and frame index. Right, fine. Now let's go back here, and what we're gonna do is frame index. And every time we're done with the frame, we're just gonna say frame index is equal to, well, what the heck, is equal to frame index plus 1 modulo in-flight frame count. Cool, perfect. And now what we got here, well, we just want a reference, really. We don't want to move anything. And here we're gonna give it the frame image acquired, I think, image available semaphore. And there we go. Look at that, so clean. All right, perfect. And after that, when we're done, we're basically gonna go ahead and say swap chain dot present. Perfect. Perfect, perfect, perfect. So now I can actually do, but before that, in fact, we need to wait for the in-flight fence. Yeah. So let's see. So in the GPU again, we're gonna need another function called wait for in-flight fence. So wait, or wait for fence, pretty much. And you're basically gonna give it an RAI fence, and it's just gonna wait for fences for you. Right now we're just gonna, you know, ignore the return types. And that's pretty much it, I believe. Wait for fence, and of course, I almost forgot once again. Let's find this here. Whoops. There you go. Now here we could use it. So let's go back to the renderer, I think. Render. And before we do any of this, we gotta wait for fence, in-flight fence. But why we can't use the GPU here? What? Are we not storing the GPU? Yeah, apparently we're not. Interesting. So let's do that. GPU. And let's initialize that. Let's make sure to initialize it first. Oh boy, this is spaghetti. This is Italian spaghetti. Let's see. I really hate these initializers, but I don't got another option. All right, perfect. That works, I guess. They'll wait for fence, and we're good. Now we wait for the fence, then we acquire the image, then we present. Let's call this image index. And let's go here, present. We also need some other things, I believe, maybe. So set swap chains, well, yeah, we need the wait semaphores. Yeah, so set wait semaphores. The wait semaphore. And I believe after that, maybe, no, you don't. Okay, cool. So where are we gonna put this? I guess here, fine. So VKRAI, semaphore. Well, wait semaphore, let's call it that, why not? And there you go, perfect. We could organize this a bit here, and we're good. Now let's make sure to kind of update the signature real quick. And there we go. So now let's go to where this thing is being used. It's being used in GPU CPP, no? Wait. This needs to be this way. Let's go back to the render now. Where's render CPP? There we go. Acquire image, present. Okay, let's go here. And here we're gonna need a wait semaphore. So we have two options. Either to... Actually, no. Let's just get the wait semaphore, really. Let's just do it. Wait semaphore. And of course a reference, not owning it, right? And let's update again the freaking thing. I really hate these kind of like separate header and separate implementation. Like, it really splits my brain in half, because every time you want to change something you have to do it twice. Extract qualification. What do you mean? Really? What does that even mean? I have no clue. What this means. Oh my god. Oh my god. Anyways. Alright, let's go back to the render right now. Render, where's render? Here we go. Now we could basically give it the frame, render finished semaphore. So we need to wait for the rendering to finish before we present. Alright, cool. And what's next? I think right now we're good. Next up, we need to also reset the freaking fence. I forgot about that. So we're just gonna basically copy this guy, but we're gonna call this reset fence instead. Reset fences. And this just takes, I guess, the fence. There we go. Now we need to kind of create the declaration, yeah. Perfect, lovely. Alright, cool. Now that we got that, we could go back again to the renderer. Where's render? Here we go. Now, after we acquire the image successfully, we're gonna basically say GPU reset the fence, please. Reset the fence in flight fence. After that, here we could actually start rendering, I believe. The real rendering happens here. So for that, what we're gonna do? Well, we're gonna grab the frame command buffer. the graphics command buffer, and first of all I think we're gonna reset it, and then we're gonna begin recording to it. Graphics command buffer begin. Oh, there is a parameter here. Okay, command buffer begin info. Dot set flags. Is there some interesting flags here? Ah, one time. Let's go with that. Why not? Flag bits. E one time submit, because we're gonna submit it once and then we're gonna reset it, so that's good. And of course, anything that you begin, you have to finish to end. And there you go. Now we could actually give commands to the GPU finally. But first of all, we gotta basically transition the image layout and to a clearable state. So we're gonna create a little helper function in the GPU again, or should we? Honestly, let's just do it inline for now. Fine. For now, let's just do it inline. Let's go back and let's just do this. So transition image to transfer. The transfer source, no. Transfer destination, I think, for clearing, I think, yeah. Let's see if the AI does this good enough. And so top of pipe to transfer. And then image memory barrier, perfect. From indefine to transfer DST optimal, then transfer right. Perfect. Yeah, done it right. And these zeros are optional, so no need for them. And that's basically it. So we're transitioning the image to transfer destination. Now we could basically clear the image. Let's see if the AI would do this well. Well, image layout, transfer DST optimal, blah, blah. Yeah, it did it, perfect. Though, actually, no. Wait, yeah, it did it, perfect. Lovely. All right, next up. I'm gonna transition the image to presentation. Finally, it's helping out. Let's see what it's gonna do. Oh, wait, what? No. So it should go basically from transfer DST optimal. But wait, what the heck? No. Ah, yes, from e-transfer to bottom of pipe. Gotcha. Yep, that seems to be fine. And image sub-resource range. And there you go. So it's transitioning the image from transfer to bottom pipe, transfer DST optimal. Present SRC, transfer right, and that's perfect actually. I think that's maybe it really. Let's try this out. And let's, oh yeah, I forgot something, hold on, stop it. We need to actually, right now we recorded the command buffer, we need to submit it to the GPU though. So how are we gonna do that? Well, let's go again here and say auto GPU, and then basically like submit command buffer, I believe, and like you just take the command buffer, and then we're gonna take the queue, our graphics queue, and then we're gonna submit submit. And what this takes, why it doesn't work? Oh, it actually takes Viki submit info. All right. And also it takes a fence. So this is the kind of in-flight fence, right? But we could just take a fence here. So vacay area I, fence, and what else? So here we're gonna set like the command buffers to command buffer. Yeah, perfect. And next up we're gonna need is, so basically there's some, we also need like which semaphore to signal and which semaphore to wait on, basically. So let's actually add it. So vacay semaphore wait and vacay, or like wait semaphore, right? And then vacay semaphore signal semaphore. And there we go. Now what's up? So we're gonna set the wait semaphores to our wait semaphore, and then we're gonna set the signal semaphores to our signal semaphore. Is there anything else? We also need this wait DST stage mask, and I believe that's pretty much done. Yep, we just need this DST stage mask. Wait DST stage mask. Alright, so how are we gonna do this? Vacay pipeline stage flag bits, wait DST stage mask. Perfect. So whoops, actually just do this maybe. Can we? No, we can't. Let's just change the type, fine. And there we go. Perfect. And I think that's pretty much it. We could organize this a bit, and we should be done. Perfect. Now let's just add this declaration of this guy. So it just takes a command buffer, wait semaphore, a signal semaphore, a wait DST stage mask, and a fence. Though this guy needs to probably be dereferenced, and same thing with this guy too. And we're good. Perfect. Now let's go back to our renderer. Where's our renderer? Alright, and what we're gonna do now. So after we end in the command buffer, which is we're doing here, right? We're gonna submit it. So GPU submit command buffer, and let's see if the AI figures that out. Kind of. Wait stage auto wait stage is equal to this guy, and yeah, there we go. So we give it the graphics command buffer, we wait on the image available, then we start rendering, and then we signal the render finished semaphore, and that's pretty much it. Lovely. We could also add a helper function to simplify this gigantic crap, but other than that, they should be fine. Yep, I think we're good. Let's try to run this and see. And I mean, what's happening there? Let's grab our Wiki config GY to grab the validation layer to see if we're missing anything. Validation. And let's see. Something's weird here. Is it at least, let's debug this and see what's happening. Is it at least, getting into the render function or not? Doesn't seem like it somehow. it is stuck somewhere. For some reason it's stuck somewhere. Why? Oh, we're not actually calling render. I forgot about that. Okay, let's go back to our app finally. And our app, things are very simple. So in the iterate function here, we're gonna say render. Really that simple. Oh, okay, I guess it works. I think it works. Though I can only verify by one way that I usually do. Which is to go to, well, where is it? Our render, right? Where is it? There we go. And let's actually use red instead. Red. You can't really mistake red. 0. And there we go. There we go. But we have a little problem. Must have been created with vk. Okay, let's go to the swap chain implementation, I think. Right. Actually, who's using this? Here. Okay, cool. So here, what we want is, instead of transfer, actually we want transfer DST here, really. That's the first thing. First validation problem. And the final one is this guy. This validation error have just been added to the validation layers. I mean, our application right now is just fine, but the validation layers are much more stricter. So even the tutorials, any tutorial gonna fall off Vulkan, you're gonna find this error, but we're gonna fix it using some extension. We're gonna use either this, or we can try to figure out how to do it with this method. So like either this method or this method. I tried before this method and it was so easy, but I'm not sure how efficient it is. Let's actually ask ChatGPT. Which method is more efficient? Let's see what it's gonna say. I'm gonna come back in a second. All right, back. Short answer B is the better design when you can use it. Longer answer with sharp edges. What B actually gives you? Maintains let you pass a fence to via the driver signals that fence was the presentation agent sticker. All right, that's so cool. So we're gonna go with that extension then. It's a new extension. Both patterns are effectively free. Okay, pyramid semaphore pools cause more object management and trickier. Now, what I'm struggling to kind of... Actually, yeah, I see. That's so cool. Yeah, let's go ahead and use this one. So it would basically make sure, because like this was just a hack that we weren't actually like waiting for the presentation engine to you know, finish. Which honestly as a beginner was very confusing to me. Like, what the heck? How does it even work? And it turns out it actually doesn't work. It was just a hack that worked back then. And it's still working. It's just that the validation layer is more strict about it because someone had some issue with that in some advanced case. But it was working just fine for, you know, usual cases. So let's use that extension. But like, let's see some information about that extension though. I think it got promoted maybe to core at some version, right? Let me see. So, did it get promoted? Or should I just... I mean, if it got promoted, they would usually say it here. So I guess I would just have to maybe enable it and that's it. Yeah, I think so. Yeah, I think we're gonna need to enable it. Did it, or we could just ask ChatGPT again. Did it get promoted to core just here? Okay. Well, then we gotta basically enable it, sure. So how are we gonna do this? Well, let's go to the device creation. Where is it? The device creation. Where we're creating the device. Here we go. So we're gonna add an extension here called swap chain maintenance 1 extension name, I believe. Right. And then what we're gonna need next. Let me ask it how to enable it. How to enable it. So I don't have to like run around. I did make it work before, and so we're gonna do it again. Come on. I hate how like all tutorials and stuff like have all this ceremony of checking like if the extension exists and so on. The thing is, the device would just, you know, not like it would fail to create like if the extension is not there. So why even check? Why even bother? But anyways, so as you can see, that's good. So we have done that. Now we're gonna enable the feature flag apparently. The feature flag, and we're gonna use the chain. Here it's trying to use the pnx, I believe, or something like that. I don't know. Either way, that's what we're gonna do. So let's see how we're gonna do this. Well. We're gonna say, I believe, chain, structure chain, right? Yep, exactly. And of course we're gonna have vacay. Well, first of all, device create info, that's for sure. And then we need the swap chain maintenance feature ext rkhr, yeah. There we go. Device create info chain. Now here, instead of creating a new one, we're gonna say this dot get vacay device create info 0, and we're gonna edit that. Perfect. Next up, what we're gonna do is device create info chain dot get, and we're gonna get this feature right now and edit that. And let's see what we got. So set swap chain maintenance 1 to true, and we're good. Perfect. Is there anything else? I think we're good, yeah. Perfect. So now that we enabled that, what's next? I think we just yeah, we just create a new fence for the present fence. So let's go to our renderer, our frame resources. So we have one in-flight fence right now. We also need a present fence, right? And of course we're gonna create it. So where we're actually using this frame resources. Find usages. Apparently it's not as straightforward, interestingly. All right, let's go here. There we go. And right here, we need to create a new fence. So gpu.create fence. And there we go, I think. There we go. So now what we're gonna do with this fence. So instead of waiting just for in-flight fence, we also need to wait for the presentation to finish. So we're gonna wait for both. So how are we gonna do that? Well, we need to get a span of fences, pretty much. So instead of this, I guess maybe we could say, I believe, span of fences, maybe? Would it even accept this? I don't know. I mean, maybe. All right, let's see. Whoops, like this? Is that the case? I mean, it seems fine with it. Huh. No, that doesn't make any sense. Hold on. Does this build, first of all? So I don't waste time. And no, it doesn't work out. So then what we're gonna do, we're gonna try to maybe copy this signature here. Yep, let's copy that signature. And yeah, PK array proxy. And we're gonna do the same thing. I'm gonna change the signature. Next. Thank you. And now I think this would build. And of course we want to wait for all the fences. Perfect. So now how are we gonna do this? So we basically want a frame in flight fence, and we also want to wait for the frame present fence. So we want to wait for both. That's the first thing. And do we even need like the in-flight fence anymore? Since we have the present fence now, do we still need the in-flight fence? I think so. At least from last time, that's what I've done. But just making sure. That's weird. Anyways, let's just do it the way I think I would do it. We're gonna also, of course, change this to AK array proxy, reset fences. You're gonna pass in here fences. Let's change the declaration to match. What the heck? Cancel, dude. What the? Let me just do it myself, please. I don't know what it's blabbing about there. Anyways, so now I could go back to the GPU. Sorry, the renderer. Where is it? The renderer CPP. And now what we got here? Let's apply this operator. And also, well, basically, I'm just gonna copy this guy, right? Gonna copy this guy. Next up, in the presentation part. In the presentation part, we also need apparently to signal something. So notice that the presentation wasn't signal anything, but right now it would signal the present fence. Now the present, it would have like a signal fence, right? So this would be, of course, a RAI fence, signal fence. All right, perfect. So now how are we gonna do this? Well, we also gotta change this guy right here. Oh my god. Okay. Fine. Good things takes time, I guess. All right. So we got the signal fence. Now we basically need what? I think we need to chain this now. Yeah, we pretty much need to. So how are we gonna do this? VK structure chain. And here we're gonna say swap chain maintenance. Whoops. Maintenance one. No. Present signal or signal present or what is it called? I don't know. Let's see. Does it say so here? I guess. Yeah, there we go. Is that it? Yep. Swap chain presents fence invoke HR. Now I'm gonna do the same thing here. So like this, and then .get vk presents invoke HR. And then here I'm gonna say this. Take this. There we go. Now we could set the fences to signal. I noticed it says swap chains. What the heck? No, that just what? Let swap chain count. Right, fine. Let's just say set fences here, and we're just gonna have one fence because we have one swap chain. Signal fence, and there you go. Done. Has no member, so let's change the signature to match. I mean, come on, dude. Let me just do it myself. Thank you. And let's do this. And there we go. Perfect. Now who's using this guy? Wait, no, this is, let's dereference that and we're good. So who's using this? Probably the swap chain, I would guess. So swap chain CPP, and we're gonna give it the signal fence right now. Perfecto. And we're just gonna change this definition right now. There we go. And finally, we're gonna go back to the renderer. And right now it works. Perfect. So this is it. So we're basically waiting for the fences. We're resetting the fences and then we're presenting. I think that should work, yeah. And it shouldn't have any synchronization problems anymore, hopefully. Oopsies, failed to validate extension in list. No freaking way. No way. Not supported. I'm pretty sure I've used it before here on Wayland. What the heck? Really? Let me see. Like Vulkan. Whoops. Vulkan. Really? No way, dude. No way. No way. What is it called again? Okay, swap chain. God damn, dude. I don't have it. Really? I'm pretty sure I've used it before. Oh my god. So that sucks so bad. That sucks so bad. Did they remove it or something? I should have used Git. Oh my god, dude. Oh my god. You know what? Nah, that's gonna suck. Let me just manually do this stuff, right? So we don't have any present fence anymore. Oh my. We could keep the goodies, the refactoring of having like accepting multiple fences. That's nice. Other than that, gonna remove this present fence here. We're gonna go to alright. We have no signal fence anymore. No signal fence. GPU HPP. Where's the signal? Here we go. Let's remove it. Let's remove it from here. And let's just do this directly pretty much. This is so sad. Oh my god. There's also another extension that would have made my life way easier, but it's also not available on my system for whichever reason. I don't know. And I'm on Arch Linux, so like Cashy OS, so basically I have the latest of the latest drivers. Well, that's wild. Anyways, fine. Where are we gonna need to... I think we also need to change the device creation to remove this extension right now. And, I mean, we don't need this for now anymore. And there we go. And we're back into square zero. Value is never used, fine. Let's see if this runs. I think these were all the changes that we've done, right? Oh yeah, this one too. Let's remove the screech fence here. And we should be good. Yeah. Alright, fine. Okay. I wonder how much time we've been... Alright, 3 hours. Alright, let me see if the live is even still on. I don't know. Let me see, where is it? Here we go. Okay, the live stream is still on. Okay, cool. So let's actually, I guess, maybe go to shaders and, you know, draw a freaking triangle. But hold on, I'm not gonna do my mistake again. Let's use git, please. I don't want a disaster. Git branch -m main, fine. And let's set up git real quick. Let's set up a git ignore. Dot git ignore. Let's add this. And let's say ouch, ignoring the ouch folder. And ignoring probably .idea. And that's pretty much it, I believe. Now, of course, we need to version all these files. We need to add them. So let's add them to Git, add to VCS. And now this is our clear screen or clear window, right? And we're gonna commit all these. Oh boy. And yeah, set and commit, and we're good. So if anything flops, we could always go back to this place. Like a lot of time, the reason I was like, I stopped some like series just because I flopped the source code and I can't go back. Oh my god. Alright, so I think we're good now. Perfect. Now we could easily do whatever the heck we want and we could easily recover. Perfect. Now, one thing before we actually go to the next step, which is like drawing a triangle, let's just simplify some few things. For example, this pipeline barrier here, we could simplify into one little helper function into the GPU, in the GPU. So notice that right now we used all these abstractions. Notice our render function, it's quite simple, and it would be even simpler when we're gonna abstract this thing. Look at this crap. This whole thing just to, you know, transition the image layout, which is wild. So let's add a little helper function in our what is it called? In our GPU, I believe, right? Graphics command buffer. Do we have access to the device from the graphics command buffer, by the way? We do, but not like the real device though. Okay, because like there's the RAI version which have the dispatch table, so we could call functions on it, and there's the VKD device one, which is just a regular handle which doesn't have the dispatch table. But anyways, so what we're gonna do now, let's see. So we just need the graphics command buffer and we need the image. So maybe we could even do it on the frame. What do you think? So like frame. Let's try. Select the frame. Where is it? Frame resources. This guy. So let's see. So like transition image, I guess. Transition image layout. But like this is the let's do something like this and basically generate the definition here. And let's go. So graphics command buffer, the pipeline barrier. And yeah, that seems to work. Actually, love that. And we just need the VK image first of all. And that we want to do. Change signature to match this definition. We'll see about that. And I also want another thing, which is, so first of all, let's just change the signature. Fine. Next. Fine. Never mind. And yeah, let's go here. And I'm gonna create a little struct here, which is gonna contain something here. So image state. And I'm basically gonna have a vk image layout, and then a vk access flags, and a vk pipeline stage. And I think that's basically it, right? Yeah, I think so. Right. So, and also I'm just gonna call this maybe transition image state, right? And the thing is here, you're basically gonna give it an image, right? And you're gonna give it an old state and a new state. That's basically how it's gonna go. And I'm gonna show you what I'm gonna do with this in a second. So like if we go back here and here, and well, where's that? Let's grab the signature real quick. Let's go back. Let's put it here. The new signature. And that should work. Huh. Oh, we changed also the function name apparently. Yeah. And there you go. So we go from the old state.stage to the new state.stage. And same thing with it. We just ignored the memory barriers in this is just for the images. And we only have one image for now. Set old layout, set new layout. SRC, DST, set image, sub-resource range, and we're good. You may want the sub-resource range too though. But for now, let's just keep it hard-coded, I guess. This could bite me later on. For now, let's just keep it hard-coded. Okay, so let's see where we're gonna do this. So let's go back to our render right now. Where's the render? Oh my god. Okay. Now, instead of this business right here, oops, what did I do? I have no clue. So instead of this, we're gonna comment this out, and we're just gonna say frame transition image state image, comma, this, and there we go. There we go. It's really that simple. So instead of this business, you just have this business. And since these are structs, what we could also do, we could go to our struct and like we could define some presets kind of, right? So like you could have, let me just copy these presets for example, and we could go here and like, let's see. So for example, you could have an image state, present state, and it would return this. and then an image state, initial state, fine, I guess. And then what else? So these are like the, well, this is like present state though, huh? Weird. Honestly, this is just none, basically. None. And to be honest with you, none, I think. Yeah, fine. None, and what else? We're also gonna need clear. So image state clear. Yep, perfect. And that's honestly all the states we need, I think. So none, clear, and present. Let's order them right. Why not? And we're good. Now you see what we could do here right now is, if you go to render, the old state would be, instead of this business, we could just say none, I believe. Well, this should be static, really. Static and no consts. And this one also static. And honestly, can we move the definition? I think so. Yeah, perfect. Huh. Move definition. Move definition. I start to become more productive with C-line right now, that I kind of start to get the hang of it. But anyways, so now what? Now what? So instead of image state this, we're just gonna say clear state. And clear color image, and then afterwards, instead of this business, we're just gonna say frame transition image state from the clear state to the present state. Though we can actually rename this to just present, really. And there you go. Look at that. Beautiful. Nice. Way much easier to see what's going on here. Way easier. Perfect. What else? What else? I think we're good now, right now. And of course, we still have the same code. And honestly, oopsies, cancel. Come on, terminate. Honestly, I'm just gonna amend this commit, and we're good. The other thing we should handle is like the resizing, but right now let's just go straight to the shaders, honestly, so we can render some triangle. And to do that, we need to compile some shaders first. So how are we going to compile some shaders? Well, we're going to need a shader compiler. Now we could either compile shaders offline or online. I'm going to show you how we could do them online. And for that, if you have VC package, it is very easy. You're just going to say shader C, add to VC package, and you're good to go. Now it's going to add VC package into my project, though it's going to need to build it right now. Though it's kind of heavy, so if you don't want that, then you just got to compile it offline using the command line. But for me, I don't care right now. And right now we need to figure out where we're going to steal the shaders. I think we're going to steal them from the tutorials. And let's just create a triangle dot vert add and triangle dot frag add. And then what we're gonna do is let's check out the Vulkan tutorial real quick. Throw in a triangle. Drawing, I think. No. Graphics pipeline basics, I believe. Shader modules, yep. And let's just steal these. Let's steal this for the vertex shader. And let's steal, well, actually for this, yeah. And for the fragment, we're gonna steal this. It's basically just like, you know, instead of having to create a buffer, which I'm gonna show you too using VMA. But for now, let's start simple. So we're basically gonna have like positions and colors in the shader itself without having a buffer, right? It's just like an array of vertices, right? The array of positions and an array of colors, and here we're just using them. Pretty much using GL vertex index. And that's pretty much it, very simple. Triangle frag, nothing fancy, or just, you know, redirecting the frag color from the vertex to the fragment. Of course, the GPU would like, you know, make a gradient out of that, but yeah. And my computer is going crazy right now, and hopefully it doesn't crash or anything, because, oh my god. As you can see, it's quite heavy, because like it's gonna compile that crap from scratch. Hopefully it doesn't crash my computer, because it did. Oh boy. Hopefully not. First of all, please, let's close some programs at least. And let me just watch out for the temperature, because I have some temperature problems with my CPU. And the compilation uses all the cores. So B-top. Yeah, look at that, 92C. That is wild. Let's just, oh my god, 94. Oh boy. Let's pray it doesn't crash. Because like, if my computer shut down, the live stream is gone. Hopefully not. Oh my. Okay. We're saved. We're saved. Alright, cool. So now it built everything we need. As you can see, you don't have to mess with CMake or anything. Right now, you're just gonna copy this, go to CMake, come here, paste, and done. Just copy this, remove that, paste it here, and you have shader C in your project, linked and ready to go. Perfect. All right, so now how are we gonna do this? Well. So who's gonna first of all have our compiler? Who will have the compiler? Well, of course, our GPU, I guess. Yes, let's go with the GPU, fine. GPU. So we're gonna include here shader C. I guess shader C.h maybe, I don't know. I guess we'll find out. And we're gonna have our compiler. So where are we gonna put it? I have no clue. I guess we'll just put it here, why not? Alright, and that doesn't work. Maybe it's something else, I don't know. Weird. Oh, shaderc.hpp, I think. There you go. Perfect. Okay, so that works. So this would create a shader C compiler. Now we could use it. So how are we going to do that? Well, let's go to... So we're going to create like a function, essentially, that would go ahead and do this. So auto compile shader. It's gonna like take an std file path, file system path, and it's gonna take, I think that's pretty much it really. Well, it's actually not as easy because like it needs to hold a lot of crap. Let me think about it. Should we create a new class for it? Yeah, I think so. But let's do it here at least. First of all, shader, and we're gonna like have a class here or struct or whichever. Shader, which is gonna contain a few things. So we're gonna have first of all an std vector for our code. And what else? And we're gonna also have a shader module, and we're gonna store the pipeline. Yeah, I think so. I think that's good. Is there anything else? I don't think. That's all we need, I believe. And here we're gonna basically do this, and hopefully the AI would do the first part for me. Let's see. So the first thing first, we need to open a file. So, well, what the heck? File system, file. Wait. No. I think fstream, right? If I remember. Or iStream or fstream, apparently, yeah. Yep, and we need binary and 8. Binary because, well, we're reading binary, not text. And second, 8, so we would start like at the end of the file so we can get the size of the file. Now, let's include fstream. And the next thing, we're going to make sure that it's got opened successfully. Yeah, failed to open shader file. And what's up? Fine. And now we're gonna get the size. Yep, there we go, tell G, and then we're gonna go back to the beginning of the file so we could read it. We're gonna create a vector buffer, and then we're gonna read that buffer in one go. So you see, this is why I started at the end of the file, so we could use tell G, so it tells me where I'm at, which is the end, so it's basically the size. Then I'm gonna go back to the beginning of the file, and then I'm gonna create a buffer that is that size, so we don't have to like reallocate every time, we just allocate once. And then we read in one go, one system call, pretty much. And now, if that doesn't work, failed to read shader file. Other than that, what are we gonna do next? We're gonna basically try to compile this. So compile, well, what? Shader compile, and let's see what we got here. So we got assemble to SPV, and compile GLSL to SPV, and compile GLSL to SPV assembly is valid and pre-processed GLSL. I'm just gonna go, I guess, to compile GLSL to SPV, and here we need the source text and the source size. So we're gonna basically say buffer dot data and buffer dot size and all that cool stuff. Right. There is a little allocation here, but you kind of need it, at least in Windows, because like you have a Unicode kind of crap. In Linux though, it doesn't matter. You could just like get straight a CSTR, but it wouldn't work like when you hop into Windows, it wouldn't work. So let's just keep it that way for now, I guess. Anyways, and what else? So would this return, oh yeah, it would return a result. Okay, fine. So we got this result, and let's see what we got here. Okay, compilation status. Get error message. It's like OpenGL, right? So yeah. Okay, compile status. Let's see. Yep. So if it's not success, then we're gonna throw runtime error. Failed to compile shader. Next, what are we gonna do? How do you get the actual compiled stuff? Oh yeah, you have this CND and CBegin and stuff. Like it's like an iterator essentially. Okay, and there you go. Perfect, lovely. And there we go, there we go. There we go. Whoops, something went wrong here. Wait, what? I'm confused. So let's just remove that right now. And yeah, there we go. We got the code. We got the compiled code. So like this is the SPV assembly. And next up, what we're gonna do, we're gonna need the shader module create info. Now, well, honestly, I'll just create a shader module directly. So device create shader module. And what this would need, a shader module create info. So let's go ahead and do this. And let's set the code to our code. And there we go. Now, this would give me the shader module, basically. So module. Perfect. Set code. What else we can do? I think that's pretty much it. It's like the shader module just like, you know, like wraps that code binary. Next up, we're gonna assemble the stage info and stuff. And honestly, here we're kind of hard coding it to fragments, but instead of that, what we could do instead is we could have a variable called shader kind, right? And so how are we gonna do this? Well, I mean, let's see, we could honestly come here and do it. So shader kind. So if, yep, there go ahead. If path.extension equal to .vert, then we're gonna select vertex shader. Otherwise fragment shader if .frag extension. We could also include their compute if we ever use that. We're probably gonna use it soon for post-processing, though maybe not in this live stream. But who cares? Anyways, compute shader here, and we're pretty much, I think, good. Right? And supported shader extension otherwise. And yeah, now we're gonna use this instead of hard coding that stuff. And also another thing that we want is the actual vk shader stage flags, right? So we also need that. Now for that, we're gonna need to, we can't really go by using that anymore, unfortunately. So we're gonna do this and that and this and so on. Now what we're gonna do, stage E vertex, stage E fragment, and stage E compute. There we go. Perfect. And what else? And that's pretty much it. Now what are we gonna do? Are we done? Let's see. So of course we're gonna move the code there, and we're gonna move the module. So move ownership, of course. And the stage info, we're gonna set the sure. Set module, set pname, main. We're just gonna hard code it to main. Who cares? We're not gonna use specialization info either. And yeah, that's basically it. There we go. No, wait a second. No, this wouldn't work really. Yeah, this wouldn't work because we're gonna be like, you know, referencing some data that could be that is moved. Yikes. So instead of doing that, please make sure to do it this way. Just store the stage only. And we're gonna assemble the other struct later on. So that's pretty much it, unfortunately. And yeah, so let's go ahead and say stage. There we go. Perfect. Perfecto. And that's our compile shader function done. Perfection. All right, so what's next? Let's see. Let's see. Next, we're gonna need to create a pipeline. Pipeline. But let's actually create shaders first. And the real $1,000 problem is, where are we gonna create this shader? Well, good question. I guess the application probably. Yeah, probably you want to do in the application. It doesn't really, like, you know, every renderer could reuse the same pipeline, you see. So that's basically it. Right, so let's go to our application here and let's go here. And before we even create the render, why not? We could like, actually, yeah, pretty much. So let's go ahead and do this. So we're gonna need the shader. So like shader of, like, this is the vertex shader. I still can't really. Anyways, fragment shader. So basically we have two shaders. But of course, both should be optional. And okay, so after creating the GPU, let's go to this guy. So after creating the GPU, we're gonna say vertex shader dot in place, and what this guy needs. So GPU compile shader. There we go. GPU compile shader, and boom. One thing though to make sure is to set the freaking, let's see, the working directory to the project directory. And I just gotta copy this guy. Let's see, copy path reference, absolute path, come here, boom, edit, working directory, boom, apply, okay. And now this should work out just fine. It should compile our shader, both vertex and fragment. And we should go to the next step, which is creating the freaking pipeline shader. And there we go. Perfect. Perfecto. Though one thing that I want to do, by the way, is always before quitting, we want to say GPU wait idle, kind of. So how are we gonna do that? Well, honestly, for the GPU, really, yeah. Or I don't know, either way, who cares? Right now, how are we gonna do this? Good question. Wait idle, I guess, or something like that. I don't know. And here you basically say, well, let's avoid that trap again. And let's say here, how are we gonna do this? Device wait idle, right? Yep, there we go. And let's of course move the definition, and boom, there we go. Now let's go back to our application, I believe, and here we're just gonna say app GPU wait idle. And there we go. Now it's gonna make sure to wait for the GPU to finish its work before quitting the application. And that's pretty much it. Just to make sure we exit cleanly. There you go, perfect. And that's basically your shaders right there. They're loaded and compiled successfully. Next up is the pipeline. So how are we gonna do that? Well, good question. I don't know. Just joking. All right, let's see. Let's create the pipeline here. Create graphics pipeline. And the graphics pipeline is a whole huge blob. of stuff, and hopefully the AI could fill in the blanks real quick. Because I'm definitely not doing all that. Let's see. Shader. Now, honestly, we'd probably better off making the shader from now. Maybe. For now, honestly, fine. Let's just keep it this way, really. Who cares? Let's go with, this is like the vertex shader, and this is like the fragment shader. And that's basically it for now, I guess. And let's see. So now how are we gonna do this? Create graphics pipeline. So here we need the pipeline cache, which we don't care about right now. So we're just gonna say nothing. Next up, the vk graphics pipeline create info, which we do care about. Next up, null ptr, we don't care. And that's pretty much it. Now, let's see what we got here. So, let's see. Oh boy, that's gonna be a lot of crap. I'm thinking if I want to use some extension for this, or... Well, first of all, let's make sure to use at least dynamic rendering. Though, let me see what kind of extensions I have, though. Shader. I like vk, khr, shader. Right, or what? So these are all the extensions I have available in my GPU. I don't think I have that shader thing, I believe. Yeah, I don't think so. Like pipeline, there's binary, pipeline library. I do have pipeline library, but shader, nah. Yeah, so let's just only use dynamic rendering right now. How are we gonna do it? Well. Dynamic rendering. So when we're creating the device, right? Where's the device? Here we go. And we need to basically add a feature there. And we're gonna need that vk swap chain, not really, structure chain, right? And one of them would be this. And the other would be vk physical device, I believe. Vulkan 1, probably 3 features. Right. So this is your device create info. Right, and we're just gonna basically say .get vk device create info. Why this doesn't work? Whoops, what the heck am I doing here? There we go. Now here we're gonna say .get, and we're just gonna basically give it this. Well, actually this, and then here we could just say set dynamic rendering, basically. Dynamic rendering to true. And we're good to go. So here we basically enable dynamic rendering, so we don't have to worry about render passes, which are even wilder or crazier. But that's basically how you enable dynamic rendering. Next up, let's go to the Let's go to creating the actual graphics pipeline right now. Oh boy, this is gonna be a marathon. Let's see, dude. Set the modules. Can we set the shader stages? I guess, yeah, stages. So set stages vertex shader, the shader module. Though we don't, I guess, need that. Though honestly, this one we could just call it module, really. And same thing here, fragment shader dot module. Though what the heck is happening here? Really? Let's see what we got. So this is your stages, right? We don't really need these. Oh, that doesn't work out. How do you... Huh. How do you create a VK optional that is empty? Oh, you just pass in null PTR. And yeah. So this would give us back a pipeline, I guess. And we're gonna basically return it, I think. Right. So return the vk area pipeline. And there we go. Okay. So now we got the shaders, the stages, and what else? And in fact, even the stages, like, we could maybe try to just put them in line here. So everything in one place. How about that? It doesn't work. Well, apparently it doesn't seem like it. Yeah, it doesn't. I don't know why. Anyways, next step, what we're gonna need. Set what? Oh yeah, we're gonna need the pipeline layout too. Oh my god. Set layout. So we're gonna need a pipeline layout. So basically vk area pipeline layout, pipeline layout. There we go. And we're basically gonna have like an auto GPU create pipeline layout. And that's basically it. And honestly, this is very easy. We could just create a declaration. Really, we don't need anything fancy here. And yeah. Now here, we're gonna need this guy. So we could just take, you know, a reference really. And what else? Dot set, what else? Stages, viewport, render pass, blah, blah, blah. Let's just right now follow up with the validation layers really. It's gonna tell us what we're gonna need really. So I guess let's create a declaration. We also gonna need something else though, which is like the viewport. Sorry, the dynamic state. The dynamic state, dynamic states. So auto or like std array, dynamic states is equal to that. Viewports and scissor. And there we go. What else? Well, actually, why that doesn't work? There we go. It's a dynamic state like this. Cannot convert an L value of type to parameter const. Why? This is so weird. Is that how it goes? Yeah. Apparently. Well, that kind of suck. What if we just do it directly here? That works. I don't think though for this one. Or is it? Not really. Okay, fine. And I think that's basically it. Maybe let's just try. Though we gotta have the validation layers on though. And also we need to actually call this function first of all. So let's just stop this. Pretty much. And let's create the graphics pipeline right now. So let's go to our application here and we're gonna have a graphics pipeline. So std optional graphics pipeline. Well, vk REI graphics. Wait, not really. Pipeline. Oh boy, pipeline. There we go. And then we're gonna need an optional vk REI pipeline layout. There we go. And here we're just gonna have this pipeline layout. And there we go. And what's next? So let's go to our initialization function here. And after creation of our shaders, I'm gonna go ahead and say pipeline layout in place, create graphics pipeline layout, and then I'm gonna create my graphics pipeline using my shaders. And there we go. Yeah. And there we go. And I think that's basically it. Now we just gotta basically make sure that our validation layers is up. So to do that, we're gonna go with vk config GUI, yeah, and no, and let's go to validation and run. And now we're gonna know which parameters we need that are missing. So I don't have to specify all the freaking parameters there. Yeah, there we go. It just segfaulted right there. Okay, cool. Oh, what the heck? Invalid? What? Invalid vk shader module object. Why? That's wild. The one thing we could also do here is break. And could click on debug and it would break straight into the code. So the debugger is quite slow, which really sucks. Yeah, no way. Never mind. So let's see what we got. Let's see. Why the shader modules are empty. Create graphics pipeline. Um, So we're creating pipeline layouts, we're compiling the shaders, and then we're in placing. I don't know why it would be invalid. Let's set the other stuff first of all. Dot set, well, not here apparently. I guess maybe here. Okay, dot set vertex input state. P like vacay vertex input. Pipeline vertex. No. Apparently not. So vertex input state, fine. Next up is the multi-sample state. And next, you got the rasterization state. And that's, I guess, pretty much it for that part. The other ones are probably optional. So, multi-sample state. And rasterization state. I think fill is the default, yeah, so no need. Though we probably do need the topology or something like that. Maybe it's not here. I don't know. Hold on. Yeah, I think maybe the topology is here, possibly. Let's see. No. Where's the topology? Weird. But I guess we'll find out with the validation layers. Alright, so that's pretty much it, I believe. P input assembly state, sure. I think this is the one that have the assembly thing. So, Yeah, there you go, triangle list. And is that it? Let's check out the rest of the validation errors. Line width, rasterization state. Set line width 1. And we need to set the viewport state apparently. Okay, fine. Oh, what the heck? There we go. And bruh. Set viewport count 1, set sitter count 1. Is that it? Alright, so we're done with those ones. Now I just need to figure out why the heck is the module is invalid. Alright, so we're getting the vertex shader. And we're getting the fragment shader. And we're passing them here. Okay. And here we got the shader. The shader is code vector. We got the module. Okay, I can already see where this is going. Alright, that's the first thing. Second thing, where this is being used, let's see. Well. Yeah, I think we're fine. Alright, let's see. Okay, perfect. So now we finally got a graphics pipeline. Now what's next is just to bind that pipeline and freaking draw 3 vertices. Oh my god. Okay, so how are we gonna do that? Well, oh boy. Where is that? App event or? My brain is fried. Like fried chicken, dude. Alright, so app CPP. Yeah, we need the render function. Okay, where is the render? Engine src include render. The render function. Okay, dude. So instead of clearing the color image right now, first of all, the swap chain. Oh boy, we gotta also make the freaking image views. Okay. okay. So std vector vk REI image view, image views. Hopefully the AI could do this very quickly. So let's go ahead and do this. Let's see. Images. Member is inaccessible. Oh boy. Alright, so let's go to our GPU real quick and let's add a function to create an image view. Okay. What we're gonna need? Yeah, I think that's pretty much what we're gonna need. Let's go back. Where is it? GPU. HPP. So just the image and the format. Okay, fine. So let's generate the definition real quick here. And let's return that. Perfect. Lovely. Now let's go back to, where is it? Swap chain. And here, instead of this business, I'm just gonna say create image view. Perfection. So we're going through every image in our images, and then we're going to basically create an image view, and then we're converting it into a CD vector. And there you go. Though maybe we could do something interesting here. I don't know. Maybe something like a CD bind front, possibly. Right. Is that the case? I don't know. I'm just seeing how this would go. You could do something like that. Huh. You could also even, you know, do something weird like, I don't know, like G is equal to, this is basically called currying, I think. Bind back. Whoops. Bind back. And like you could say F, comma, vk format. And then I believe you could probably just like, I don't know, just say G. Maybe? Would that even work? Doesn't seem like it. It's kind of weird craziness, but no need. No need, no need, no need, no need. Yeah. Alright, so that was a crazy detour. Other than that, so we got the image views, perfect. But now, instead of the vk image, we don't really care about the vk image anymore, but we do care about the vk image view instead, because we're going to be rendering. Alright. Alright. And so we're going to use the image views here. And the vk area image view, and of course we're going to return just a reference, really, here, I believe. Right? Is that true? Like this, yeah. And wait, what? This should be vk area image view reference. How about that? There we go. Perfect. So what's next? Now let's go back to our render. And right now, instead of an image, we're getting an image view. And we don't need these transitions anymore, right? Well, actually we do. I forgot. So let's see. So vk image for the image, and then an image view. Can we even do this? Huh.
Bruh. Oh yeah, my bad. Like city pair. VK image and VK image view. Though. There we go. Perfect. And now how are we gonna handle this? Wait a second. Okay. Now let's see what we're gonna do here. So return image images image index comma image views image index. Though for the image views you're gonna just give a reference, I think. I'm kind of confused here. Whoops. Oh boy. Let's remove that. And there we go. So now we need to figure out how this works. Okay, so that works. Perfect. So what's next? Now let's go back to our render. And so here we're basically going to take two things. We're going to take the image and the image view, which is great. Now next up, instead of clearing the color image, well, by the way, we're going to go back to the swap chain, I believe. So like the gpu.cpp. And instead of transfer DST, we're going to say eColor attachment. And because we're not going to be using the transfer command anymore on the image. And here in the swap chain, well, where the heck? Hold on. Render.cpp. And so here the image stage, we're going to go with, instead of clear, we're going to need a static image stage render. And let's generate a definition here. Return color attachment optimal, color attachment output, color attachment right. And there we go. So now let's go back into our wherever we're using this clear and so on. There we go. So now instead of clear, we don't want that anymore. We want render. And same thing here, we want render. And then instead of clear color image, what we really want is begin rendering. So we're using dynamic rendering, not render passes. And so vk rendering info. Let's see what we got. So set offset, set extent. And here we need the swap chain extent. That is interesting. Let's make it, I guess, I don't know, this time let's make it yellow. Or fine, let's go with green. And here, honestly for now, I don't know, maybe I'm just gonna hard code this extent. I just want to see something real quick. Yeah, let's just do it for now. Okay. Now after begin rendering, of course, you gotta end the rendering. I guess, right? Yeah, there we go. And now what? Now let's actually, we can actually like set the pipeline, I believe. Let's see. Well, we actually set the viewports first. We don't need these. We don't need this. Though, do need this. 800, 600, max depth 1. And probably you also need the scissor. And finally we bind the pipeline that we have. What the heck it's trying to do here, I have no clue. Oh yeah, we need to grab the command, like the pipeline from the user, I guess. So let's actually do that, I guess. So pipeline. So like graphics pipeline. And there we go. Frame graphics command pipeline dot. Now after we do that, I guess we could just draw, yeah. Draw 3 vertices basically. And we're done. Okay, cool. Now we're gonna change the signature next. Or actually cancel, fine. And let's just come here, here. Whoops. Here. And there we go. So now where we're actually using this guy, we're using it in the render. Sorry, in the application. So application, here we go. So the application should give us the pipeline that it have compiled. And there we go. So the moment of truth. Let's see if we got a triangle. There we go. It works. It freaking works. Lovely. Alright, so the other thing that we could also set here is the clear color value. We could grab it also from the user. And for that, what we're gonna do? Why do we even have this? Weird. Oh, there's also depth stencil apparently. Okay. So like honestly, this clear value, we could just grab it and like do it there. This eStore, it's just 0, so we could just remove it. Fine. The offset, no need, it's zeros. And here the clear value. The vacate clear value. Though honestly, no. Keep it as it is. And let's say clear color instead. Clear color. Right. Or honestly, you know what? Let's say GLM Vic4 color. Really. There we go. Now. Oh, we can't do that, huh? That's weird. But I guess we could just do this then. Color 2, color 3. And there we go. So the graphics pipeline, the clear color, And what else? Well, for now, I guess that's basically it. Now, let's just add this. And let's go back here. Comma that. And I believe I could just do this. And there we go. So we could go maybe with 0.1, 0.1, 0.1 for a little dark color. And we should be good to go. Well, that's not too dark. Not dark enough. No Vulkan executable, please. And there we go. Looking perfect. And we could easily change the shaders without recompiling or anything. And that's great. Next up, let's see what we could do. Yeah, we need to add buffers. And to add buffers, we need VMA. Otherwise, it's not going to be like, you know, very good in terms of allocations, essentially. So, let's see. VMA. Is the stream fine, by the way? Yeah. Alright, cool. So first of all, let's actually just commit this. So we got all these changes to make a freaking triangle. So we added the vertex shader, fragment shader, pipeline layouts in the pipeline. And yeah. We added shader C. We added a dynamic rendering feature. Create image view. We created image views for the swap chain. Crazy graphics pipeline. Look at that. And compile shader. Render. Image state. We begin rendering, so declaring the color image. And yeah. Crazy stuff. And of course the shaders. And we added shader C here. So this is like, you know, triangle. And we're just gonna submit all the changes. Alright, so let's add buffers. To add buffers, what we're gonna do. First of all, we're gonna go back to VC package again. And we're gonna add VMA. Vulkan memory allocator. Yep, let's add that. And let's see how we can use that. Vulkan memory allocator. We're gonna read the documentation real quick. So, quick start. And we're gonna need this stuff. But first of all, let's check out the VC package stuff. It added that, but how about the CMake? There we go. We're just gonna take this guy and go to CMake lists. No, actually this, yeah. I'm gonna go here. And we're gonna come here. And also let's link the Vulkan headers, why not? Just to make sure. Really. Let's do it first. And yeah. And let's just copy these. And let's put them here. And we're gonna need a few things. The first thing is Yeah, these ones right here. We're gonna need these. So let's see. Make it get instance proc-ddr. Make it get device proc-ddr. So I'm gonna have a little break and then I'm gonna come back. Let's see. I'm gonna come back in a second. Okay, back. Alright, let me make sure everything is fine. Mic is on. Alright, perfect. Oh boy, that was wild. So far, what we have done, we've basically done like a Vulkan triangle pretty much with dynamic rendering. And what else? And the like runtime shader compilation using shader C. And now pretty much we want to handle creating buffers, vertex and index buffers using VMA, Vulkan Memory Allocator, which is the closest to creating OpenGL buffers. Because like just going straight ahead and allocating Vulkan buffers yourself is very, very wasteful, you know, in terms of memory. You need a good allocator for that. Which we're basically going to use Vulkan Memory Allocator for that, right? So that's pretty much it. So far what we've done, let me see. As you can see, we have added the Vulkan Memory Allocator, which is great, as you can see, in VC package and CMake. Perfect. Now we actually need to write some code. So let's just close all the tabs to start off. And let's go. Alright, let's see where we go. Where to go. So this would go in the GPU, right? So the GPU class. And oh boy, wait a second. We have this implementation, the compile shader in the header. That's wild. Let's actually move it. Move definition out of class scope, and C-line would do that for us. Perfection. Next up, is there anything else like that? No? Cool. Alright, perfect. Alright, cool. So we're gonna add here VMA allocator. So how are we gonna do that? Well, how are we gonna go about it? We can either create for its own kind of like class. It's gonna suck. Nah, not really. Yeah, no. Let's just create it in a unique PTR, really. But before that, we need the header, right? And for the header, we don't need fstream here, apparently. And let's make sure this is building, by the way. Let's import fstream here instead. Alright, cool. So basically we need to define these two. Define VMA static Vulkan function 0, static dynamic Vulkan function is 1, because we don't want to use the static loader. We want to give it our own functions. So how are we going to do that? Well. Let's go to... what can I say? What can I say? So we're gonna have it here, right? And then in our GPU CPP, we're gonna do the same exact thing, right? But here in the CPP file, we're gonna make sure to define VMA implementation. What the heck? Wait, what is it called? Yeah, VMA implementation. Make sure to define that in the CPP file only, because you have to define the implementation only in one place. Other than that, we're pretty much good to go, I think. Now, let's see how we're going to basically do that. So we're gonna need the VMA allocator. But of course we're gonna use std unique ptr, really. And we're gonna have decal type VMA destroy allocator. Okay, fine. Now what's next? Let's actually initialize this allocator. So how are we gonna do it? Well, after creating the device, I believe. Well, let me see where we're creating this. Okay, here. Let's say allocator dot in place, or reset actually in this case. And then we're gonna basically see how we could like create an allocator here real quick. Yeah, we're just gonna basically like copy this. I just, you know, nothing fancy. We're just creating an allocator real quick. And here, make sure to use your Vulkan API version. Right now we have no extensions enabled, so we're just gonna avoid that for now. It's basically you can go ahead and like enable extensions for VMA so we can be more efficient, essentially. But right now we're not gonna bother with that. Other than that, here we need the physical device, of course the raw handle. So we're gonna do it this way. Same thing with the device, really. Same thing with the instance. And there we go. This is how you basically get the raw handles from the VMA, VK, HPAP, RAI handles. Alright, so what's up with this guy? Something is weird here. Why? Ah, I see. Never mind. And here the Vulkan functions. Here you give it the Vulkan functions. In our case, we can get the Vulkan functions from where? From our dispatch tables in our RAI objects. How are we gonna do it? Good question. So let's grab our instance. And let's grab the dispatch table. Dispatcher. Okay, let's make sure this is this. Oh, what the heck? Wait, no. What? There we go. So you get the dispatcher, and then you get the instance proc ADDR. Next up, so like basically as I said before, every RAI HPP handle already gives you dispatch table, which is amazing. Next up is this. So you don't need Vulk, you don't need any of this business, you don't need the dispatch tables, it's just done for you, pretty much. Next up is the, well, where is this? Device, right? Again, get dispatcher. Huh, wait. Get dispatcher. Why that doesn't work? Weird. Oh, there we go. And here we're gonna say VK get proc ADDR, device proc ADDR, and there we go, and we're gonna pass it there. Perfect. Now, physical device, cool, lovely. Now after we create the allocator, we don't need this. This would be done for us by the, oh, hold on a second, what the heck? So we don't need this. It's gonna be called by the unique PTR for us. Other than that, after we create the allocator, we're gonna go ahead and push it into our own allocator unique PTR. And so it's gonna get destroyed automatically for us, which is great. And yeah, but there's a little problem here, I think, maybe. You need to remove the PTR of this. Remove pointer T. And there you go. And this should work. and just do this. And there we go. Now I guess this could fail. So let's say if not equal to vk success, then fail to create VMA allocator. Perfect. And now that we have done this, right now we could actually do allocation. So could you say what project are you currently working on? I'm basically making a game engine using Vulkan. Currently you can't really say it's a game engine, it's just like a Vulkan renderer. So we have this GPU class, which kind of have, we also have like shader compilation at runtime using shader C. We have, we're using SDL3 for windowing and input and other stuff. And yeah, that's pretty much what we have currently. Right now we have just basically done, what is it called? First of all, we cleared the window, then we made a triangle, and now we're basically implementing buffers using VMA, which is a very efficient allocator for Vulkan. And that's basically what we're doing. If you guys have any questions, please let me know. Alright, so we created an allocator, great. Let's make sure everything's running fine so far. Yeah, the allocator is correctly done. Other than that, we're gonna start creating actual buffers. The vertex buffer, we're gonna fill it with vertices. There you go, perfect, lovely. And let's go. So where we even start with this? Let's see. So first of all, we're gonna need like a buffer struct here, just like the shader. We're gonna have buffer, right? So this would contain two things. It would contain our vk area buffer, and it would contain our allocation. Now for our allocation, we're gonna use a unique PTR for that too. Wait. VMA allocation. There we go. But hold on. Yeah, that looks about right to me. Maybe. Yeah, I guess we're gonna see about that. Other than that, let's create a function called create buffer, or like staging buffer. So auto create staging buffer. Now, how are we gonna do this? So this would give us back a buffer, and we basically tell it, well, it's gonna have a like a template, because why not? A template. Class or type name T. Actually, templates kind of suck in headers, so for now I'm just gonna ignore that really. Let's just do it the Stone Age way. So let's just go with size T size. And what else? Actually, let's go with std span data, right? Let's go to std span. But wait. You know what? Let me just make this and see how we're gonna go about that. Fine. Alright, so in fact, let's go to documentation here, and here we go. And in fact, I'm gonna go to, let's see, main page. Recommended usage patterns, staging copy for upload. There we go. And wait a second. I'm just gonna basically take this code, copy it, come here, go here. There we go. Now we don't need this. What operating system do you use? Is it Void Linux? Linux. Arch Linux with Cache OS. Cache OS. I'm using KDE. So we basically have like a board scheduler, which it should be faster for better interactivity, and offers a variety of scheduler options, including blah blah blah. And they're all compiled like to the latest, architecture. So like most operating systems basically only compiled, in a conservative instructions, not using the latest most modern instructions of x86 CPUs. But this kernel right here that Cache OS uses, which is basically Arch Linux, but of course modified, compiled, in another way. It's basically doing that, yeah. Pretty much, and yeah. It's also using LTO, which is crazy, PGO and Bolt, and even core packages like, let's say, the compiler is also being compiled the same way from their own repositories, which is amazing. All right. Other than that, here, how are we gonna do this? So, I think we're gonna say allocated.get. Yeah, there we go. Perfect. Now vk buffer, so here's the size, and here we have our data. Data. So how about we say span of std byte data, right? And then we basically say data.size, and here data.size. So we're basically mem copying stuff. Change signature next. And I guess that's basically it. Also, we want the usage, or actually no, in this case, well, yeah, let's go ahead and do that. So vk buffer usage flags, buffer usage flags. Now let's use that here. And what's up? vk buffer usage flags. How about that? No, that's weird. Why it doesn't allow that? Weird. Should I just like do static cast or what? I mean, I guess. Maybe. Alright, so here usages and stuff. We don't need this stuff right now. We create a buffer, then we create a buffer here. Alright, so that seems fine. Here we could actually use std mem copy. Other than that, we're good. We're pretty much good. Yeah. And there we go. So right now let's create some vertices. So how are we gonna do this? Well, let's go to our application. Where's the app? Here we go. And let's go to here. So why do you use C-Line? Have you tried our IDE, Vim for example? I tried NeoVim, I tried Qt Creator, I tried all sorts of IDEs, but there's no better IDE than C-Line, let me tell you that. I tried also Visual Studio multiple times. I would rank the IDEs, first of all C-Line. Second, Qt Creator. Third, I would say NeoVim or VS Code. I would say NeoVim. Fourth would be VS Code. And fifth would be the Visual Studio. That's with my experience at least. So, yeah. Alright, cool. So where are we gonna do this? Let's see. Yeah, Visual Studio last place, definitely. Definitely. Their IntelliSense really suck. Really suck. Really, really suck. It like breaks very quickly, especially with macros. If you have macros, you know, you're done. You're done, dude. Actually, using NeoVim is good. I tried like LazyVim, I think. What is it called? LazyVim. Yeah, LazyVim. It was pretty nice, but I was used already to like IDEs and such, and also, you know, there's nothing better really than C-Line for C++, honestly. Unless if you really want to go the extra mile with NeoVim, then yeah. Other than that, let me see. Where are we gonna create the buffer now? Let's see. So the render.hpp, right? So we have graphics command. Well, not really here. App.hpp. So we have a fragment shader and a vertex shader. And well, I guess we could make a buffer here. Right, so std optional buffer, vertex buffer, index buffer, and there we go. Now here we could like load our vertex buffer and index buffer. So starting off by, well, honestly, I'm gonna go ahead to the tutorial so I don't waste a lot of time here with some basic crap. Let's just go to drawing, actually vertex buffer, I believe. There we go. And we're just gonna, you know, steal this vertex struct. We have GLM already, so it's good. And what else? And we're just gonna steal these vertices too, wholesale. And we're gonna add this get binding descriptions. There we go. It's really nothing fancy, it's just some boilerplate crap, really. Most of it, at least. So let's go ahead and see. Let's also copy this. Attribute descriptions. And pipeline vertex input. Oh, so this would go to pipeline vertex input. Okay. Gotcha. How about this binding description, right? So let's add that. And yeah, that's basically it. All right, let's see what we got here. So first of all, let's just make a vacay vertex instead. So the C++ version, kinda. Right, so next step is like here. We got vacay vertex input. Vertex input rate, e vertex, though this is 0, so we could just ignore it. Same thing with the binding here, at least the first one. And yeah, that's basically it. You just give it the stride the size of the vertex. The next step is here, the attribute description. So this basically describes the the attributes that we have in our vertex. So the first one is basically pause. So it's basically vec2, red 32-bit, green 32-bit, s float, because well, this is float as you can see here. And the offset off. So this is a macro that basically calculates the offset in bytes of a particular field, in this case pause, from in the vertex struct, right? And that's basically how it is. Now this one is the first one, so we don't really need that stuff. We don't need these either. And for this one, we don't need binding. It's just 0. And yeah, and that's pretty much how it goes. Now let's actually change this to vk vertex attribute description instead. And here we actually want to say instead, let's see, there we go. Well, actually no. It doesn't work apparently, huh? R30, G30, S float. Perfect. That's the C++ way of doing it. Though, wait. Same thing here, I guess. But here we're gonna say B32. Other than that, honestly, I would rather do it this way. Oops. Oh, what the heck did I do? Wait. What? Alright, let's remove this. And let's do it here, here. And so the format is equal to that. So that dot set format, I believe. Set format to this. That's the first one. Second one is that. And we're gonna set the location, of course, to 1. And we're gonna set the offset to offset of vertex color. And that's basically it. Now we don't need this business anymore. And we could just return this. In fact, we could probably just maybe return this like directly. Yeah. There we go. And that's basically it. There we go. Cool. Lovely. Next up, what we have else? This one, same thing. We could set the stride here, I guess. To size of vertex. And we could just return it. Yeah. There we go. Perfect. Alrighty. We have some weird thing with the allocation stuff, as it said. Probably have some problem with this, I would guess. We probably need to remove the pointer from this. Actually, no. Well, I think VMA free memory is more complicated. Yeah, I just remembered. VMA free memory is quite complicated, actually. Like, it takes an allocator, then an allocation. So you're gonna really make, you know, deleter for that. Let's see how that goes. Using, first of all, I think using pointer. Or, hold on. Well, let's start simple actually. Void operator. So we're gonna basically store the allocator. Right, so if allocation and allocator, then we're gonna basically free the memory allocator and allocation. And what's next? I remember like doing some using pointer thing. Honestly, I'm not gonna waste time on crappy documentation. Let's just ask ChatGPT. Yep, there we go. I knew it. So that's cool. That's pretty sick. So like when you're not managing like a raw pointer, you have to tell it that using pointer is equal to a VMA allocation. And there we go. Or we could just copy this whole thing and there we go. Cool. Then you can declare unique VMA allocation. Fine. Let's just grab this shamelessly. Where's that? Alright. Apparently, I guess there. Oh, no way. Wait. Did I just remove the allocator? Oh god, no. That's not what I meant. Let's do it here actually. There we go. Perfect. Perfect. So does this build? Well, so far I guess it would probably build. Yeah, it did. Cool. Alright, great. Great, great, great. So what are we gonna do next? Well, we're gonna create a buffer. So how are we gonna do that? Well, GPU.create buffer. Staging buffer we called it. And here we're gonna give it the data. Huh. STD is bytes. STD span. Can't we just like, you know, pass vertices directly? No? I don't think so. Takes CD span. Because before I used templates, but since I have headers right now, it wouldn't really work out that well. So for now, let's see. So it said that it should be trivially copyable first of all. Let's assert that, why not? And then it said basically that I could just do it this way, CDS bytes. CD span. But this doesn't really seem to work. By the way, first of all, this could be just like an array really, comma 2. And I think maybe I know what's wrong with that. Wait a second, what's going on here? Bruh, just say this. Just say this, and this, and this, really. There we go. I think what's wrong with this is that this probably should be const. Maybe. Is that it? No? Doesn't seem to work out. Let's see. Well, I guess let's see what it's going to say about that. Oh, I changed the... Okay, hold on. I think I changed it there, but I didn't change it here, yeah. I was like, bruh. Does that work now? Yeah, it does. I knew it was the problem, but I forgot to change the header too. So, there we go. That's cool. Other than that, what are we gonna do next? So we created the staging buffer, great. Now we need to probably store it though. And we're gonna basically say vertex buffer dot in place, GPU, right? Whoops. Is that it? Yep, probably. Next up, we also probably gonna say std array indices, and there we go. Now let's create the index buffer dot in place, create staging buffer, index buffer usage, perfect. And that's basically it for that part. Now we need to make sure that I think our pipeline layout probably, or is it? No, I think the graphics pipeline. Yeah, I think so. So basically something like, I guess, vertex get attribute descriptions and vertex get binding description, I think. Well, let's see this guy. So I think input, no, vertex input say maybe. There you go. Say vertex attribute descriptions. And honestly, I guess maybe I'll just copy that. Thank you so much, Even Kim. That's fine. Thank you so much. Where are you from? Okay. Where is it? Yeah, there we are. Right? No proxies, I think. Korea, I see. Welcome to the stream. So I'm not sure how we're gonna do this. Attribute descriptions. So this takes vk vertex input description. Vk vertex input description. Oh, attribute description. Okay. So you know what we could do? We could say that std span this. So this is the attribute description. Attribute descriptions, right? I guess. And then we probably could pass it up here. And that works. Perfect. Next up, we need the vertex at binding descriptions. And same thing here. So we got vk vertex input description. Bruh. Vk vertex input binding description. So std span vk vertex input binding description. Binding descriptions. There we go. And attribute descriptions. There we go. And now we could just pass it up. It's 3 a.m. Korea, so I unfortunately have to go to sleep. Come back to visit again next time. Have a great time. Thank you so much, Ivan. You're welcome anytime. Thank you so much. Attribute descriptions. Binding descriptions. Let's go. Well, say it. Vertex binding descriptions. Binding. There we go. And we're good. Right. Alright. Now we just gotta fix the signature. There we go. And now let's figure out this guy. Cannot convert R value of type. What it was? Hold on, let me actually build this. Parameter type std span vk vertex input attribute descriptions. Wait. This should work. Let's ask the AI. Maybe I should just like wrap in std span. I always forget about this one. I really always forget. So like, whenever you use that, always use const if not needed. So let's change the signature real quick. I guess right now that would work probably. Right or no? Well, that one did work. But this one I probably, yeah, because it's like just one. So I probably gotta make sure to do something like this maybe. Actually that doesn't really work out. Alright, let's do something interesting. Which is that. How about we make this an array though? Would that work? Yeah, that works. Nice. Though, how about even a span instead? Not really. So yeah, let's just keep it as an array. Fine. That's pretty much it, really. So that's cool. Alright, so now we're creating a graphics pipeline with the proper pipeline layout, vertex shader, blah blah. We're creating a vertex buffer, creating an index buffer. Now in the render should be able to use this. So, So every render, I guess maybe we need to pass it up. Maybe. Vertex buffer. Index buffer. Is that the case? I think so. So in the render function here, we basically have like a buffer, a vertex buffer, and buffer, index buffer. There we go. Perfect. Now what we're gonna do essentially is, before we draw, we're gonna bind the vertex buffer, and we're gonna bind the index buffer. And there you go. That's cool. So let's change the signature here real quick. Whoops. Next. And that's basically it. Vertex buffer, index buffer. And the final thing maybe here is how much vertices. So vertex count. Actually, in fact, since we're going to be using an index buffer, we need, instead of draw, we need to use draw elements, I think, or actually no, that's OpenGL. Draw indexed, yeah. Draw indexed. And we need the index count here. And there you go. So index count, you could just say that. And let's just make sure to change the signature real quick here. And then we could go back to our app.cpp. And here we're just going to say 3 vertices right now. If everything goes well, if I haven't forgot anything, oh boy, what's up? What the heck is happening here? Why these are gone, bruh? I have no clue what happened there. Okay. I don't know what happened there. Anyways, let's see if this works. If it works, then we have buffers working. And boom. It doesn't. We have some weird SDL. Oh well, we're gonna have a lot of fun debugging, huh? Honestly, LDB really suck for some reason. I'm not sure why. So you know what? Let me try to change it. Let's see. Where's the tool chains? There we go. Instead of LDB, let's go GDB, please. You don't have it. Fine. And let's just restart the IDE. Alright, let's see. How about now? Can it find it? Yes, it does. Perfect. Now let's try to debug this. Hopefully GDB would save us. GDB. Alright. Honestly, maybe I should clean up my project and... yeah, let's do that, I guess. Bruh. It doesn't do anything. That's weird. That's very strange. How about... I don't know. Let's see. How about I set a breakpoint? We hit the breakpoint, at least. Why it's super slow? What the heck? Bruh. Why is it going through assembly? Are you kidding me? This is weird. How about we try GCC instead? Why did debuggers suck? This is weird. Bruh. You know what? Let me try something. Let's remove this whole ouch folder. Because something's strange going on here. Now let's try to build this. I have no clue why it goes straight to assembly. Like, bruh. This is wild. Well, let me try to figure it out, I guess. Could it be the byte stuff? I mean, maybe. Actually, I remember this SDL from somewhere. It happened to me before, I believe. Oh, I guess it was when I didn't return from a function that was supposed to return. Yeah, let me see one thing. Hold on. So return. In place, is trivially copyable in deceased. Create stage in buffer. Render. What else? I think nothing fancy here. Oh well, this is just CMake, of course. And what's up with this? Nothing fancy here. Wait. Oh, we actually push it in the other end, okay. Okay. Here we're checking spans. And here we're creating staging buffer. Okay. Render CPU. Let's see. That's very strange. Well, let's try something, which is to not create any buffers for now. Oh, whoa, okay. Wait. I just remembered. Wait a second. Wait. Alright, so... Wait. I think I know what's the problem. We haven't actually changed the shaders just yet to account for this stuff. Yeah, we haven't. Is that really the problem? Let's see. So let's steal the new shaders. Where are they? Let's see. So this is the new shaders, I believe. Okay, let's shamelessly steal them real quick. And where's the fragment? I think fragment should be the same, yeah. Yeah, I think so. Yep. Now, what's going on here? Finally, try. After all those days. Oh my god. Let's see. Still interrupted by signal. Oh my god. Alrighty, great, amazing. Let's try the tip that we got here. Add compile options. app.cpp. Oh, oops, not that. Let's go to CMake. Hopefully that would fix the debugging. Cause like it's really not helping at all. Alright, let's see. How about we debug now? Yeah, probably still not helping. Oh, there we go. Okay, so it took some time apparently. And we have a problem here. Oh boy, that was wild. Oh my god, yeah, I knew it. I freaking knew it. I'm not returning something. Come on, dude. Like, come on. Like, can't the compiler actually tell me that you're just not freaking returning anything here? Like, bruh. I knew it, that was the problem, but like, I couldn't really... God damn, man. Oh my god. Come on. Really? 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 Bruh. Alright, fine. And there we go. So buffers are working. Let's go. And since buffers are working, we could do some cool stuff with async, huh? Let's see. Or we could tell ChatGPT to, you know, generate some weird shape to render. All right. All right, let's try this out. So 24 indices. And let's try that out. And we're not getting anything. Maybe the winding order or something? Though it did actually mention that it's triangle fan. It's a fan. Could it be the case? Let me see. Fan, where's... well, triangle. No, topology. Where the heck is that? Wait. Yeah, I think it's in GPU. Hold on. Engine... Triangles. There we go. Triangle list. How about we use triangle fan for a second? Let's see if that would help by any chance. Come on. I wonder if GDB is slower. Maybe GDB is slower. Sorry, like GCC or whichever. And this still doesn't work apparently, so I don't think that's the case. Or maybe the winding order, let's see. Where's the winding order? I forgot where it is. I guess maybe here. No. Where's the winding order? Maybe here? Not really. So what the heck? Where is it? That's weird. Weird. Clockwise. Vulkan usually calls back faces with front. Yep. Yep. I knew it. I mean, come on, I just want to like... Bruh, how do I change the order? Let's see. I can't believe I forgot how to... Oh, there we go. Wait. Sit front face? Come on. No, it doesn't work. No, just pick the list. Alright, let's remove that crap, honestly. And let's go back to where we're doing that stuff. Wait, we're doing it here, okay. So let's just say Control Z for now. So this works, right? Oh, I think maybe I understand what went wrong. It's trying to... Wait. Go back? Yeah. Bruh. Come on. Yeah, I think GCC is probably way slower than Clank. Okay, so right now at least we're getting something. But let's try this new one that it gave us. And see. Give it another chance. but let's make sure that this is 32T and 30 vertices or indices. Oh, we set the index count to, oh, okay, wait. Let's actually see this first of all. A lot of freaking foot guns, oh my god. There we go. So our buffer is working, great. So if you do, also let's go back to whichever shape it generated at first. Let's try it again, hold on. Let's try the first shape it tried to and see what was the problem there. First of all, it should be UN32T first. And second of all, let's make sure to change this to 24. Let's try now. Oh boy. There we go, it actually works. Lovely. Lovely. Alright, now let's just go back to our triangle. Let's just go back to our triangle. Or, yeah. Maybe we could try right now async to Lloyd meshes. Async. Should we try async? Well, actually, first of all, let's try to add some uniforms though. So how are we gonna add a uniform to, like, you know, rotate the triangle, for example? How are we gonna do it? First of all, let me switch up my toolchain real quick, because GCC, I feel like it's way slower than Clang, I believe. I feel like. So let's remove the ouch and let's regenerate everything just to make sure. And let's run this. Perfect. So now let's see how I could do uniforms. Let's see. So to do uniforms, it's actually not that easy. You have to do uniform buffers and so on. But in our case, we could make it easy, I believe. Wait. Push descriptors and so on. Uniforms buffer mapped. Honestly, you know what, I'm kind of tired at this point. It's already 6 hours. So I guess that was it, guys, for this stream. Thank you all for watching. So this is basically, I'm gonna actually publish this code if anybody is interested. So like, this is VMA buffers. I'm probably gonna go live tomorrow, though probably at night. So yeah, overnight, right? So like at the middle of the night, pretty much. Other than that, thank you all guys for watching, and I guess see you in the next one. Goodbye, everyone.